I hope that you got the opportunity to get this, to install it, and to run a Jupyter notebook or Jupyter Lab. And we are just in the middle of notebook number 6, I think. Of 6, yes. And at the break, for the lunch break, we were doing this exercise in the middle of the notebook number 6. If you want to catch up, you need to execute the cells before, and then we will go on from there.
Okay, so just to recall what was the idea. The idea is that we had a variable x that was x plus sine for x, if I remember well. And the idea was to integrate sine of 4x as a new column and to see if we can catch up the non-linearity patterns from the signals, and if we can make the linear model a bit smarter. So for that, I can load directly the solutions. So here we can see that in the X-train and X-test, we augment the feature by concatenating to X-train NP4 sine of X-train, and the same for the test. And now we just feed the data with this extra column and predict using this extra column and make the similar plot than here. Okay? So now when we do that, we see that the orange points can follow basically the sign, which was not possible before because we engineer a feature that grasps this sine x nonlinearity. Okay? So even with linear models, if you actually can understand or if you know something about your model that you can augment features, a simple linear model can actually answer to your question. I mean, can model precisely what you want. So that was the sense of why adding a new column. Okay. So do you have any questions or maybe?
So maybe if you consider that the model is the two-step of adding a new feature that is a nonlinear derivative of the original X-train, plus fitting a linear regression model, the two steps together, they form a nonlinear model. And this way we can basically add some prior knowledge on the problem into the feature extraction part, and then use a simple linear regression model in the end to make the final prediction. So this is why linear models are still very useful in practice, is that it's very easy to do feature engineering when you know a little bit about how the target variable and the input variable are related, and then you just use a linear model to blend all the feature together in the end.
Okay. So now we just saw a linear model, which was the linear regressions, and now we'll play with the nearest neighbors, but the regressor one. So it's working a bit similarly to the nearest neighbors, but for the regressions. So in that case, we can define as well the number of neighbors of the regressor, and we can fit and train our models on the training data. And similarly, we can already predict. So for the moment, we just predict on the train. And as we know, because we have a neighbors of 1, so we'll always have like the best accuracy that we want when we do on the training because we have the same samples. And when we find that, we see that the prediction are exactly placed on the data that we had originally, which makes sense. Okay. Now, what we're interesting is actually to do that on the testing data, and we see that the parametric model is doing natively a bit better than the linear models because it's using information from neighbors to interpolate, and somehow is grasping a bit of the non-linearity. Then we can also make the score and compare the score of the coefficient of determinations here, which is 0.91, and which was much slower, smaller here. So here it was 0.79. What we didn't try, and we could have tried here, is one that we make this. We could have checked what it was. So if I execute this, yeah, that was not a good idea. It's not the same data anymore. The X. Yeah, but because it's my X. So I want to just... Okay. And now if I compute the score...
It's XX.
Okay, yeah, XX. And here... Yeah, okay, yeah. Okay, and here I was 0.96. And here I'm still under it. So just by using, I mean, the linear model could grasp if you have the informations.
Maybe you can try with the neighbors, larger number of neighbors.
Yes, so here we can check if we increase the number of neighbors. So let's say 10 or 5. So we'll see first on the training what it changed, and now we see that all our points, I mean, we will not have an accuracy of like R square of 1. Our prediction will not be exactly what we have inside the data, but that we are still following the trend, okay? And it's a bit more regularized, so we don't feed the noise. So it looks really like a sign in that case. And then when we do that on the prediction, it doesn't change so much, but it should probably improve a bit. So we went from 0.91 to 0.94 as what we saw this morning, because we are a bit more robust to noise.
So here what is interesting is that k-nearest neighbors has no, it's a non-parametric model. It makes no assumption on the structure of the data, or little assumptions. The only assumption is that the local structure, local distances between the points is meaningful. And that's interesting because compared to the linear model, we had to do the feature engineering to capture the periodicity in the signal. And here it could automatically find this periodic structure by itself. However, keep in mind that it's not able to extrapolate the periodicity outside of the region of the training set. If we were to predict on the right or on the left, it would never find a periodic structure, whereas for the linear one, it would perfectly extrapolate because we have hard-coded that into the model in the feature and in the linear trend.
Okay, so now the idea is to use the same models, but instead of doing it on this simulated data, is to load the Boston dataset, which is a dataset for regressions, which have more features, and just use those different regressor and see what's the scoring on those. So with the train test and splitting the data and just reproducing the same thing.
So the Boston dataset is a very old dataset that is being used in statistics. It's a housing priced dataset. So the goal is to predict the price of houses in different regions, neighborhoods of Boston, based on the descriptors that you can find in the desk attributes.
So I will load the solutions. So if we just check at what we have here, so the first line now we are used to it. So first we import the modules and basically the function which will allow us to load the Boston datasets. We import the function to split And as a first try, we'll just import the linear regressions, okay? So the three first line here are just to get the data and the targets for the datasets, for the Boston dataset, and then call the things to split, okay, X, Y. So we'll keep 25% for the testing. We create two instances, one regressor specifically for the linear regressions, one regressor specifically for the k-neighbors regressor with a neighbors of 1. And then we fit our linear regressions, X, Y. And we can get the score on the training and on the testing, and we do exactly the same with the k-neighbors. We fit on the train sets, and then we score on the training and on the testing. So if we do that, we see that with a neighbor of 1, we have a score of, a perfect score with the nearest neighbors, while this is not the case for the linear regressions. However, the k-nearest neighbors is not able to generalize on the data, while it is quite a bit better for the linear regression in that case, okay? We could even try maybe, for instance, just to increase a bit the number of neighbors and see if it's changing something, and we see that we decrease on the training, but we don't overfit noise when we do that on the testing, okay? So it means that sometimes it will be useful to make hyperparameter search to search what's the best parameters for the problem that we want to do, okay?
One more comment on this. So you see that k-nearest neighbors doesn't really work on this data set. Do you have an idea of what could be a cause of the really bad behavior of that model on this data? So look at the description of the data.
You tried neighbor 3.
Neighbor 3?
Yeah.
It works?
Pretty equivalent.
Okay, it's equivalent to linear, but it's not better. Okay.
0.5.
But there are still a potential significant problem that could, yeah.
It's because the different features have different orders of magnitude.
Yeah, exactly. So those different features, they have different physical units. They vary on very different scales. So there is really no guarantee that the Euclidean distance on those units make any sense. So for instance, here you have a proportion of a residential land zone. So it's a proportion between 0 and 1. And here you have a concentration of parts per 10 million. There is no guarantee that this is between 0 and 1, or the age is between 0 and 100, for instance. So very wide variations. So some of those features would be much more impacting the distances, and others will be completely ignored. And if the ones that are varying on very low variance are actually the most predictive, they will be ignored by the model. So what we could do is do some kind of preprocessing to make sure that they're all approximately on the same scale, and also we could also remove the variables that are too noisy. This is actually the topic of the
next
notebook, how to do this kind of preprocessing.
Do you typically do that with the k-nearest neighbors?
To do scaling? Yeah. Yes, you need to have some distance that is meaningful in some way, and comparing different physical units is not meaningful. So you need to make it dimensionless. So you can choose different kinds of scaling, like divided by the standard deviation, for instance. But sometimes this is problematic if you have outliers or very weird distributions. You could also use a quantile normalization, where all the values are between 0 and 1. And 1 means that 10%, 0.1 would mean that 10% of the value will be below that. So it's some kind of cumulative density distribution normalization.
And maybe another thing is that usually here we have kind of small number of samples, and the k-neighbors is not an algorithm that will scale with the number of samples. So usually whenever you start to have much more data, you will not be able to use it. So that's
but if you have more data, it's going to be more accurate. But then in practice, very few people use the k-nearest neighbors in practice, because it needs to record the full training set. So you need to have a copy of the full training set to make a prediction. So for instance, if you want to ship that as a small model that you embed in a mobile phone, it's too big. It might be also too slow to compute the distance to all the data points in the training set. And also it can also be a problem from a privacy point of view, because if you ship the model and there is the full training set with all the data of all your users inside the model that you can decode quite easily, then it's another issue. So in practice, it's not used. The k-nearest neighbors is not very used much as a like industrial production system, but it's a very good baseline if you want to compare more advanced algorithms like random forest or something like that. It's good to, as a sanity check, to compare to k-nearest neighbors.
Any other questions before that we go? No? Okay. So next one is about unsupervised learning, which will be about some transformation. So we spoke about scaling, so we'll go towards that. And the second thing will be about dimensionality reduction through PCA and such kind of methods. Okay, so the first part will be about transformations. So we can import the top one. So how we explain here is that because different features can be scaled differently, then it can impact algorithms. So in the k-nearest neighbors, it can impact the way that you compute the distances. Some other algorithm that will be based on, for instance, gradient descent, or you will not be able to make the optimization properly. So usually you have always a pre-processing step which try to scale the features, and then you have to put a bit of knowledge there to know what the best scaling apply to your features. So one of the standard way, and that might work maybe 90% of the time, is actually to standardize by recentering the data and having a unique scale per features. So how does that work? So if we take a quick examples where we have a NumPy array with 1, 2, 3, 4, 5, the idea is to center by removing the mean and divide by the standard deviations. In this case, we'll have a unique unit standard deviations. Okay, so if we do that, then we see that the value 3, which was the mean in that case, will be centered to zeros. And if we check here and that we compute the standard deviation, it will be 1. Okay? Yeah, that's STD 0.99999, almost 1. So this is probably one of the most used, and when you have continuous feature, is probably, if you don't have any knowledge about your data, is something which is widely used. So we can try to do that on the iris datasets, because we saw that we have different height and widths. But then we can also have like different, we can be, the width is larger than the height or otherwise. So we'll probably benefit from standardizing the data first. So the first thing that we do as we do usually, we split the data into training and testing. And here we keep a proportion which I think is 80% by default.
That's what the random state is.
The random state is to be able to make the splitting deterministic. So we saw that we have a shuffling. Okay, so it means that if I execute this several times across Python, that I restart Python, then I will have different shuffling. Okay, because it is random. The random state can be set such that the results will be always the same. So it's the randomness is deterministic. So it will shuffle, but always in the same sequence.
Just an identifier, sort of. Every time you run it with that number.
Yeah, we will get the same results. So it's to be able to compare across sessions that things are the same.
So yeah, we are using internally the Mersenne twister algorithm from implemented in NumPy, which is a pseudo random number generator, and it needs an integer seed. And when you give it a seed, it will return you an object, which is the random state object. So here you can either pass a NumPy random state object, an instance of that class, or the integer seed to create that object again. And yeah, so because as we said previously, when we do the train test split, we do a shuffling before taking the train test split in case there is some structure in the labels, for instance, and we want to break that structure. So we need some permutation of the data, but we want to be able to reproduce several times the same results when we run the notebook. So this is why we fixed the random state seed. In practice, it's very important if you fix the seed to check that if you change the seed, the final conclusion from your analysis doesn't change. But it might be useful to regenerate exactly the same figures.
So imagine that
publishing result.
Yeah, if you want, for instance, to just see the impact of a classification methods, but you don't want that the pre-processing have an impact there, you will fix the seed such that every classifier will see the same data, for instance. So you can fix the random seed, or the random state for this case. So here we split the training and the testing, and then we can check what is the mean and the standard deviation on the training. So we get for each feature, so for the first feature, second and third and fourth, we get the mean for each features, and then we get the standard deviations. And it's actually those information that we will use later to rescale the training data and the testing data. So an important thing to keep in mind is that we don't rescale all the data at once. We are computing the statistic that allows us to scale on the training data only, okay? So the testing data should be kept out. And that's something that you need to be careful. Otherwise, you bring knowledge, you leak knowledge from the training, from the testing into the training. So then you can have, you can corrupt your fitting. So instead to do this by hand, what we are using is actually a module which is pre-processing, which have a lot of different scalars. One of them is a standard scalar, which is actually the one that we implemented at the first step here. So it's doing this under the hood. So to do that, we just import the standard scalars, create an instance, and then we give it the training data to learn basically the statistic of the mean and the standard deviations. And then we will transform the data. So when at fit time, it's computing the statistics. So now if we do scalar dot mean, we'll obtain the same statistic that we previously computed by hand, and exactly the same for the scale.
So why, in your opinion, why do you have 4 numbers here for the mean or the scale? Because there were 4 features initially in the data: the height and width of the petal and height and width of the sepal. And those basically standard scalar is treating all the features independently of one another. It's a univariate preprocessing that is applied independently on all the features.
So now how to scale basically the data is we'll call transform, which will use those statistics which have been learned and which transform for us the data. So we get exactly the same dimensions. And if we even print the data before and after, so for instance, I will just show the first 5 lines. And after scaling, so we got those one. Okay, so we see that basically here we have making an operation. So the operation is just removing the mean and divided by the standard deviations. And now if we check, after scaling the mean and the standard deviations, we'll obtain what we saw before. So the data are centered to 0, or to, we have a small numerical errors, but and the standard deviations is equal to 1, okay? And then when we want to make this standardizations or these normalizations on the new test, we don't call fits, we call directly transform on the data, okay? And then we see that in that case, we are not exactly equal to zeros, which is maybe normal. We didn't standardize considering only those data. We use the statistic that we computed before to standardize those ones. So we can have a slight differences. So here, this is to explain that basically we should properly scale the data at training and at testing, because if we don't do that, then here, in that case, we didn't scale the data, okay? So we scale the training data, but not the testing, and we see that compared to when it was like properly placed, they are all over the place. So they completely, they are not in the same scale. So basically, if we do a k-nearest neighbors, the neighbors are not anymore at the same location, so it will give like very wrong results, okay? So what is applied on the training need to be applied on the testing, but the statistic that need to be computed on the training, not on the testing. So one figure which give a summarize of whatever is in Scikit-learn is the following. So right now we saw the standard scalars. So imagine that that's our original data. And to show how they are, basically, we see that 0 is here, and they have like a big shift, where they are centered around 6.5 and 12.5 here. And then they don't have the same scale in X and Y. And the standard scalars just bring all those data at zeros and make that the standard deviation in both axes, in both features, are equal. And then we have a kind of like different standardizers that have different characteristics. So for instance, the min-max scalars will scale all the data between 0 and 1 in each axis. And that could be useful, for instance, when we have sparse data and that we don't want to shift our data because we want to keep the sparse entry to 0. That's one case. The robust scalars is when we have some outliers and that we don't want to take those outliers into considerations. So it will take the distant interquartile in that case.
Yeah, it's actually to compute the statistics for the scaling operation. For the standard scalar, we use the standard deviation. And for the robust scalar, we take the distance between the fourth quartile, the first quartile, and the third quartile, which means like a 20% percentile and a 75% percentile, 25 and and basically, this is interesting because assume that in the original data, you had one single data point that was much higher on one axis, and on the other axis, you did not have this kind of outlier. It means that the standard deviation across the first axis would have been, the scale would have been completely shrunk by the single outlier, and then we would not apply the same scaling on the two different axes. And a robust scalar is kind of a protection against that. It will not remove the outliers, but it will make the scaling much more independent of the outliers, of the extreme values. And quantile transformer is a bit different. It's a bit similar in the sense that it's projecting everything between 0 and 1, but it will ensure that if you have a value around 0.5, you have half of the data set that is below 0.5 and half of the data set that is above 0.5. Basically, it's using the cumulative density distribution, function of the distribution, to be able to map those data from the original space to this 0, 1 space. And this will shrink the outliers to 0 and 1. they will disappear completely if you do that. So this is a bit weird because it's not a linear scaling like robust scalar. We don't divide by a constant value. We apply a non-parametric transformation on the data that might induce some deformation, but also provide robustness against outliers. And
then the two last is the same class, so it's a normalizer, but we have different way of normalizing. We can project all the points on the, so every row will be normalized individually, and they will be projected on the sphere. So that's the L2 normalizations, and the L1 normalization will be on the diamond, basically. So they are it's a bit less used, let's say, I think. Maybe
so yeah, for instance, this kind of normalization can be useful for if you have only positive features that are count values, and or for instance in text documents, and you have a very different number of words in two different documents, but the topic should not be dependent on the length of the document, so you can divide by the total number of words in the document, and this is approximately equivalent to doing this. So it might be useful for some operations. Also, maybe for computer vision, it can also be useful to normalize by the average pixel value in a single image. So this is those normalizers, they are per samples, per line normalization, whereas those, they are per column normalization. So it's a bit different.
Yeah.
Does the scaling you choose depend on your data, your model, or a combination of both?
Combination of, so for instance, if you use trees, you will not need probably those normalizations, because the way that the model is working will not, it will not have the problem of scaling. I mean, it will learn that. And then it will depend on the data. So for instance, I mentioned like when you have sparse matrices, so you will not apply standard scalars, or actually when you have sparse matrices, you don't want to move all the zeros entry to something different, because you want to still, you don't want to basically densify your matrix. So
because a standard scalar, you will shift by the average, so all the zeros will be shifted to some negative value, for instance, and then you will break the sparsity pattern, and all the entries will be non-zero, and you will explode the memory usage of the representation. Whereas with min-max scalars, zero values will stay at zero values, assuming that all the values are positive, all the non-zero values are positive. So this will preserve the sparsity pattern and will make it tractable to represent the data in memory.
And then now we speak about like continuous data, then you have categorical data, and you will not normalize the same way as well. So it's like data dependent as well. So you have both model and data. But generally, like what you are saying for linear models and nearest neighbors, and most of the models need this type of things.
So yeah, if you assume that your data is approximately univariate Gaussian variables, and there are no extreme values, then the most common normalizer is the standard scalar, and actually some models make some assumptions that the data is approximately Gaussian with unit variance, and if you use any others, it will break that assumption. But in practice, it doesn't make that much of a big difference if you use robust scalar instead of standard scalar. If you don't have outliers, that's approximately the same. Even quantile transformer or min-max scalars, sometimes the accuracy won't be impacted too much. You can use train test split to measure the accuracy to make sure that you're not making any mistake. It doesn't impact too much the results.
Okay. Any other questions? Okay. So now we will pass to one very used algorithms which is used for dimensionality reduction, which is called PCA, so principal component analysis. And the idea is to find a projection. So for instance, if we have 10 features, is to find a subspace with much less features where those features are still discriminative. And to do that, we will find the transformation which basically maximizes the variance. So let's start. So here, just to give an idea of what the transformation is doing, here we have some original data. okay, which are basically an ellipsis which is rotated. And if we consider that we would like somehow, if there is two classes, we might want to project the data such that, I mean, basically the PCA will find the two axes, the two components where the variance is maximized. So one axis is along this axis, and the second component is along that axis. And one that we transform the data basically is just that we just rotate the cloud, okay? And then we can look at the data to a single component. So by projecting all these points into the second component or into the first component, and is what we are seeing here, okay? So it's like when we drop the second component, and here is only with the first component with back, that we back project. So if we imagine the following points, where we have two clouds, so a first blob and the second blobs. In this original feature space, we cannot basically find a linear transformation like out of the box, which splits very well the data. While when we apply PCA, so now we can apply PCA. So PCA is inside the decompositions modules. We can create an instance, fit and transform the instance, and then check what is the projections. And we'll find that what we did is just like finding the variances, similarly to what we did here. And then now we can maybe find one of the two components in which we can split easily the data, so we don't need like the two components we can keep only one component over the two, which will lead us to perfect discriminations. So for instance, in that case, we can, if we project all those data onto that axis, we'll have the violet points will have distribution around the Gaussian array around here, inside that part, while the yellow point will be projected inside this part here. So the second principal component will be very useful to discriminate violet and yellow point, while if we are projecting all the points on the first component, the marginal distribution will just overlap, okay? Because all the violet points are also, they are mixed to each other on the first component. So is one of the drawbacks of PCA, it just finds the component which maximizes the variances, but it doesn't tell you which component is more discriminant than another. So we can learn, and basically, when we are learning, we can pass the number of components that we want to keep. Okay, so here we say X blob have two features. And here in the PCA, we'll say, okay, one that I will call transform, I want to keep only n components. So in that case, we want one component, and you will keep the first component. And one that we transform, the same data, and that we check the shape. In this case, now we have only one dimension. The history.
So just to clarify, so in this case, we are using the first component, and as we've seen previously, it's a bad idea to keep only the first component. So it's gonna destroy our ability to discriminate. So in general, doing PCA might be useful because it might remove the components that are not too informative. Y equals 0 and y is equals 1. So here you see that the two classes, they are overlapped, and we cannot discriminate in that new space.
Which is equivalent to this here.
Projecting on the first axis. So PCA is fundamentally unsupervised. It doesn't use any kind of information from the Y variable. And so it's just trying to find the components that explain most of the variance of the original data layout. And sometimes, if you reduce the dimensionality using PCA, it will make it possible to remove low-varying dimensions or subspaces, and which means that it can get rid of some noise. But sometimes the actual signal is in the low-varying subspace, and so when you trim that, you might destroy the signal. So there is no guarantee. It's not a supervised transformation. So there is no guarantee that it's actually good for as a pre-processing step for a supervised model. But still, it's often very, very useful. So at least for visualization.
And this is where you have the linear discriminant analysis, which use the Y to make those kind of projections. You will use the class information, for instance. But in that case, it's not an unsupervised thing; it's a supervised one. Yeah. So visualization is a big problem because you have only usually more than two features.
So here we don't have the problem because the data is already two-dimensional, so there is no point in using PCA in that case. But if the original data was four-dimensional, here you would have put n components equal 2, apply to something that is higher dimensional, then you transform and the result would be 2. And then you can use a scatter plot. I don't know if we have an example.
There's an example on the bottom using the digits dataset. We have much more, I mean, you have like 64 dimensions, and we'll project this into 2 dimensions to plot the numbers as a visual. Yeah.
Will it give you a report where you can have it, reproject the different dimensions and then give you the percent of the variance explained by each dimension that's projected? That way you can determine if I think the first 3 have accounted for the right thing, especially the variance.
Yeah.
So this n component, if we check the help, can be either the number of components that you want, or it can be a float. I think. Yeah, it can be a float. And the float is actually the explained variance. So you can say, I want to keep 90% of the component that, I mean, the variance. Of the variance, of the cumulative sum of the eigenvectors, of the eigenvalues. Sorry.
Okay, close this.
Yeah.
And set to 2 here, and then execute it and insert a new cell and do PCA.explain variance.
Oops, sorry.
Or ratio, explain variance ratio is more interesting. So here you see that the first component is capturing 97 or 98% of the variance, and the second component very small fraction of the variance. So you can also access this information, and you can trim then the result based on this.
And I think that if you don't if you don't say anything, you have an algorithm that automatically finds the number of components.
There are some heuristics, but
sorry, yeah. Okay, so here that's the examples where we want to basically use PCA to actually be able to find how numbers are organized. But I mean, it's more for visualization purposes because we have 64 dimensions, and then plot what we can see in 2-dimensional plots where we keep only the 2 first components. So in that case, we have our data, which we already used before. So every line is a 64 vectorized images. And then we put all of this inside a matrix, and then we apply PCA, and then we reproject those data on some axes, and then we see if the numbers are glued together in this case. So for instance, in that case, on the first component, that's the first component here, that's the second component here, and then we plot the label linked to the numbers, and we see some nice plot where things are kind of clustered, so all the 0 are clustered inside that first component, the 4, the 1, couple of 2 here, the two years.
So the first component is able to discriminate between 0 and 1 very efficiently.
Yeah,
And the
yeah.
second component is able to discriminate between 4 and 2 very efficiently, or 4 and 3 very efficiently. And so maybe we can plot the actual first component. Here you see that it's something that can discriminate between 0 and 1, because this pattern of white pattern will match zeros very well, and this vertical pattern will match 1 very well. So it's a mix of a 0 and a 1, and you can see it.
And here you have the 4.
Yeah, here it's harder to see. But so by looking at the actual structure of the component themselves, you sometimes you see those are the singular vectors of the centered data.
So yeah, and as the comments say here, so whatsoever decision we took to find this new subspace, we didn't use any information about the target itself. Okay, so everything was unsupervised in these regards. So now, as an exercise, is just to load the iris dataset and to reduce the dimension from the 4 first dimension that we saw at the beginning into a 2-dimensional. And check the 2 first components of the PCA. So if you can play during 5 minutes and see what those components look like.
So yeah, project using a scatter plot, transform the data and do a scatter plot with the first 2 components, and see if we can distinguish the 3 classes using only those 2 components.
Okay, so we can have a look at the solution. So as we saw before, load the iris, train test splits. We import the PCA and the standard scalars to reuse what we saw just before here. We stratify. Okay, so first thing that we do is that we learn the standard scalars. We fit X-train. And then we create a component in which we will keep only 2 we'll train a PCA. We create a PCA instance where we keep 2 components. Sorry, and then we fit and transform the X-train, where we apply the standard scalars inside the PCA, and we do the same for the test. And then we just make a scatter plot where we just use for the 2 components. So and we go on the 3 different classes. So if we do that, we have this for the training here and here for the testing. So I don't know if it's really better or not, basically, but basically here this is the second component, the first component that we found, and it could be helpful to use the first component to identify here the intersection to identify the first class and the other class, and this is also true on the test sets, and we still have troubles to distinguish the second and the third class here. Okay, so it's not necessarily better than what we were doing at the beginning, but it's not. We don't have like knowledge by hand. Okay, this is automatic. We give the data, and it just projects the data and give us the 2 components without us to look at the data. Yeah, I saw some questions. So here we do what is called feature extractions So we are projecting the data, but we are not selecting a feature. So they don't represent petal width or height. It represents a linear combination of both. Okay? So you cannot interpret. The first plot was a bit for this here. So that was my two first feature and second feature. And here, actually, this is a bit of the first feature and a bit of the second one, because it's a combination of those two which represents the first component.
How do we get this information? What is the combination between original?
So if you go at the bottom, let's go back here. So the PCA object has a component attribute. And here, basically, you see the coefficients. So for the first component, you see that it's a positive combination of the first feature plus some smaller weight, but negative weights for the second feature, and so on. If iris.feature names, here we have the feature names. So it's this coefficient multiplied by the sepal length, this negative coefficient multiplied by the sepal width, plus this high coefficient, high value. So it's just basically making it this one negative, and the other ones are approximately on the same scale. Whereas for the second component, it's mostly positively this one, and the others are very close to zero. So actually, it's interesting because this one, the second component is almost aligned with the petal length. That's interesting. I didn't know. Actually, it's also mixed with the sepal length.
So that's where you have to understand the difference between feature selection, where you just select column, and this one, which is just a transformation and extractions, where you actually project into a subspace which is not the original one. So that's where, and in that case, this is a linear combination of those original features. And somebody else had the questions? Yeah.
So does the PCA method have a loading plot which would do this for you graphically?
No. You will have to transform the data and plot them afterwards.
Yeah, so there is very little plotting features in Scikit-learn, so you have to do it manually. Okay.
Any other questions before the break? No? Okay.
Okay, so after the break, we are gonna speak a bit more about unsupervised learning, but this time clustering algorithms, I guess. Let me check.
Yeah, clustering commits.
Clustering, and then we do a recap, and then do a more real-life scenario with the Titanic dataset, and then a bit of text classification. And so far, if you want to know, France as a one is leading by 1-0. And the pandas tutorial is taught by a Belgian guy. So
we have to go and drop by there.
Yeah.
Okay, so we can take
15 minutes.
15 minutes break. Tu sais quelle salle c'est? Okay. Okay, so let's start. First cells for matplotlib and numpy. So now the idea is that we saw dimension reductions, we saw some scaling, and now we'll see some algorithm that basically try to group together samples and try to simplify in like say in the raw directions. So the first things to understand this problem, what we'll try is to use simple blob dataset that we'll generate and try to understand how clustering is working. So let's start by creating a dataset using makeBlob, like what we did before. And by default, makeBlob will have 3 blobs, like this one. Okay. So if you execute this one, this will create the X and the Y target, which we'll not need because we are doing actually Rhino clustering, so we'll not need to transform the data. And when that we plot the figure and the scatters is what we get. So we get 3 Gaussian blobs, okay? And the first things when we try to actually cluster is that we want to have, without looking at the target themselves, just looking at the data, we want to find the group of samples that together seems to make sense. So for instance, in this case, the question I think that is under is, in this case, what do you expect when you want to make clustering in that case? Yeah, basically group each blob together. So one blob here will be one class, this one should be a second class, and this one should be a third class. So this can be done with one of, the most maybe known algorithm is K-means. And it's an algorithm in which you can, in advance how many cluster. So in that case, we know that we have 3 blobs, so we should have 3 cluster. And then we'll tell him, okay, find me the 3 best cluster that you can find. So to do that, we just call K-means and we explain how many cluster do we want. And then we can fit and predict at the same time. And it will give us back the labels. Okay, so now it means that he classify every samples in X as a label between 0, because we say that this is 3 cluster between 0 and 2, okay? One of the things is what we could think about if we plot it here. We see that actually make a perfect classifications. So for instance, those points are clustered together. This one is the second class, and this one is the third class. But if we look at a comparison between Y, okay, which is the true label that we generated at the beginning, and the label here, which were from the predictions, and that we ask him, are they all the same? He will say no, okay? So then we have to go a bit more into details why. And we could ask for printing Y and printing the labels. And here we see that 2 and 1 are not the same, so it seems that like the labels are shifted. So we can see this visually. So here we have colors. So this one is yellow colors, violet and green. And if we do exactly the same using the original data, we see that the yellow is on the bottom left, while here it was on the top. The green here is on the bottom right, and this one on the top was actually here. So because clustering doesn't know anything about the label that you have to assign, it makes sense that actually when our algorithm, even if a cluster pretty good what we wanted or it give us the results, it doesn't give the label that we expect. So it means that we cannot use a metric that we use in classification, for instance, for clustering. So because if we use the np.mean, so is what we did this morning. So if we compute the accuracy, it will tell us that we have a 0% of accuracy because none of the labels are corresponding. Okay. And this is what the case, we can even check like a confusion matrix that will check class by class and count the number of samples. So here it means that all the samples from the first class were actually classified in the class zeros. Here all the samples of the third class were classified in the second class, and and the last one, like the first class in the third class. So the confusion matrix shows us that instead to have everything in the diagonal as a perfect classifications, it just mismatch the labels.
It's basically a perfect permutation of the labels, basically. So the label values 0, 1, 2, they are just permuted, but the cluster membership, they match the expected structure. So 2 points together, if they are expected to be in the same cluster from the ground truth data, the K-means algorithm has recovered those relationships, the pairwise relationships, but they ignore the value, the absolute values of the cluster label names, but in the integer identifiers for the clusters. And this is expected because it didn't have access to those when training, so it's not a problem.
So here we already give a bit of the answer why. I mean, okay, we have a permutations. So now the question is, how can we fix it? Do you have any idea of how basically we can find a metric? I mean, what should be a good metric to actually tell us that if we have a good clustering or not?
Did you say that you should include labels in the training?
The point is not to change the learning procedure. We still want to have an unsupervised learning procedure, though. We want to keep k-means as it is. How can we fix the computation of the accuracy, basically? We don't want to use accuracy because accuracy is a classification matrix, it's a supervised classification matrix. But how can we evaluate the quality of the clustering, whether the clustering is good or not, without looking at the absolute values of the labels? We just want to assess that the grouping are correct and not take into account the absolute values of the labels. So
We can look at the distribution of distances from each of the clusters to the cluster center.
we can look at the distribution of the distances to the cluster centers. That's a good suggestion.
So the confusion matrix is just rotated. It's not.
Yeah.
It's not corrupted, right? It's actually, if you rotated it, it would be diagonal. It doesn't cross terms.
So yeah, we could try to find a rotation and see if we can have a rotation of the confusion matrix that would be diagonal. If it's the case, then we have a perfect clustering. But then it's hard if it wasn't zeros. Like if it was non-zero value everywhere, it would be hard to find. Maybe it would be possible using some PCA, for instance, something, I don't know, maybe eigenvalue decomposition or something. Yeah. Difference between the original labels and the labels and then the standard deviation. Yeah, but it would also only work if they are exactly the same. If there is some deviation, that's a bit. Yeah. What we could do is instead of focusing on the labels, instead look at pairs of data points and see if we have a pair that is in the same group in the original label information, if that pair is still preserved according to our clustering algorithm, and the fraction of pairs that are preserved, for instance. And there are many kinds of variations of that idea that can be used as clustering metric. And I think there is one here in the solution of this exercise, which is called adjusted rand score. You can look up the Wikipedia definition, but basically it's based on that idea that we try to look at pairs and the fraction of the time that a pair of samples that are in the same cluster in the original label, according to Y, are also a pair of samples in the same cluster according to the clustering labels.
So, and in the case that we use this metric, we see that we get a perfect score of 1 because, yeah, we look at the pairs and because our clustering was perfect, and it makes a lot of sense because the pairs are just preserved and only the label is changing. Okay?
So I think adjusted rand score can be negative, not sure.
Right.
If you have a random clustering, it could be slightly negative, yes. But on average, if you have a random clustering, it should be close to 0. And if it's perfect, it should be 1, exactly 1.
Yeah, it's close to 0 because it's normalized.
And if you have something like 0.5, it means that your clustering algorithm has found some repeatable structure, but it's not like very stable.
So here, everything was fine because we knew in advance that we had 3 clusters, and we just, okay, find 3 clusters. But sometimes it's not that easy to know basically the number of clusters that we have. So for instance, if we would have said we have 2 clusters, k-means wouldn't have been smart enough to actually tell us that, oh, actually you don't have 3 clusters. I mean, you don't have 2 clusters, you have 3 and change automatically. No, he would have clustered all the data into 2 different clusters. So he would have grouped together those 2 cloud of points and say, okay, that's 1 cloud and this is your other blobs, okay? So his word, this is complicated in real life to actually know how many clusters and this type of things. So here we can check basically where are the cluster located, but probably one of the cluster center will be here, and then I assume that the second cluster will be in the middle of the 2 cloud of points. My centroid will be in the middle, okay? So one heuristic way, which is a rule of thumb, okay, would be to actually try the same way that we did with the k-nearest neighbors, would be to try different numbers of clusters and then check the center of inertia. So
actually, the center of inertia, what we call inertia here, is the sum of squares between clusters or something like that. And this is actually one of the suggestions that was suggested to evaluate the quality of the clustering. And this is the metric that K-means is actually trying to minimize when it's converging.
Yeah, so it's a dispersion. So this one, for instance, have a high dispersions compared to these ones. But the problem is that if you increase in a lot of very small clusters, then you will find a very small inertia because you over cluster, let's say. But we'll see this later. So here, what we do is that we apply different number of clusters with k-means and just check this inertia, so these dispersions, and then we'll check how these dispersions evolve depending of the number of clusters. So here we have the number of clusters, and this is our distortions, and we see that after 3, okay, after 3, one that we have 3 clusters, then the inertia is a kind of plateau. So the rule of thumb would be, okay, 3 would be the smaller and enough number of clusters just to represent our data per.
So basically, this number is expected to decrease always, and it's actually still decreasing a bit. Here, the slope is non-zero. But there is a break here, and we call this the elbow in the curve. And so if you can detect this elbow, it's a rule of thumb to find a number of clusters with k-means. However, in some data set, it might not be as trivial as this. It might be like a very constant slope, and then there is no strong elbow. And sometimes you might have 2 stuff that looks like elbows.
That could be steps. And then it's difficult to know what you should select. So it's where it's a bit complicated. And some others, more advanced algorithm, actually you don't have to precise that. They will try to find the specific number of clusters. So is what the thing is saying here, you don't have, I mean, it's coming with some assumption, but basically this is difficult to find the right rules to say I need that number of cluster because you don't have any idea of how your data are organized. So, for instance, we don't have any idea of the distribution of the data, and k-means doesn't make any assumption on that. So it means that you can have like some increment number of blobs, and they will just wrongly find them. When the shape is not round whatsoever, here he will cluster all these parts together because they are close to each other, but he will not know anything about that. Basically, my density is like a kind of ellipsis. Okay.
So basically, k-means makes the assumption that each blob is approximately spherical in the original representation. It doesn't try to find. It makes this assumption that the blobs are approximately the same shape, same number of elements, same sizes, and if one of those assumptions is broken, then you see that the results of k-means are not very good.
Okay. So but k-means is one of like base algorithms. So in scikit-learn, there's a couple of algorithms, which here we call like, so you have k-means, mini batch k-means, which is not here. Which
This is min shift, the second one.
Yeah, min shift, DB scans, affinity propagation, spectral clustering, word, and here is an image which make a summary of how the different algorithm will behave on different type of data, basically that we saw before.
So, for instance, if this is a perfectly well-separated blobs, they have approximately the same number of points, they are approximately spherical. In that case, k-means work perfectly. And this is called a mini batch k-means. It's like a more scalable variant of k-means. And you see that if we break those assumptions, as we've seen previously, then it doesn't work really well. And if you have this kind of nested data structures as the first line, it doesn't work at all. If you compare to spectral clustering, which is also applying some kind of k-means, but in a eigen decomposition of the affinity matrix, of the distance matrix, this is able to find this kind of structure here quite easily. However, the problem with this guy is that it's not very scalable. It's very compute intensive, especially on large data points. Here we have some other algorithm, word and agglomerative clustering, which are two variants of what we call hierarchical clustering algorithms. And sometimes they are able to find this kind of data structure very well. However, it's not perfect either. Like for this kind of data, it doesn't work. Finally, DB scan here is a very nice in practice. It's a density-based clustering algorithm. You don't give it the expected number of cluster. It can find automatically a good number of cluster by itself. What you give it as a hyperparameter is the approximate size of the interactions between samples, so some kind of scale hyperparameter. And it's also interesting because here you see there is a violet point because it can detect outliers automatically, and it can decide to put some points as outliers. So in practice, I think dbScan, and there is a even more advanced version which is called HDBScan, that is not implemented in scikit-learn but available as a third-party open source project, which is compatible with scikit-learn. I think for many practical application, this one is very good. And there is also Birch, which is nice because it has the same nice properties as agglomerative clustering, but it's much more scalable. It can work in an incremental manner on a very large data set. So it's also useful for that. And finally, there is a Gaussian mixture models, which is a density modeling model. But it can be interpreted as a clustering algorithm that is very similar to k-means. However, it's making soft assignments. Instead of assigning each data point to each centroid, it will assign them with a probability, some likelihood value, so that you can, instead of just having colors, you could have levels of confidence. And furthermore, it has more flexibility than k-means, and it can it makes the assumptions that the blobs are Gaussian, but they can have a non-spherical covariance matrix, and it can estimate that covariance matrix also on the fly. So if the data is Gaussian, then Gaussian mixture it can be very good, and it also has some kind of confidence level. If the data is not Gaussian, like the first two, it will fail similarly, like k-means.
Okay.
So there is no good general clustering algorithm. In practice, though, dbScan is very useful for many practical applications.
So now, the idea would be to use k-means to clusters the digits images. So we know that we have 10 classes. So it would be to try to make a k-means clustering on the data. And then to visualize the center of the clusters. Okay, so we can get back the centroids, and from these centroids, just show the pictures. And then to use the adjusted random score to know what would be the performance of such unsupervised clustering.
So to do the visualization, it's a bit complicated. It's a lot of Matplotlib code, but we did it previously with the digits. But if you don't know how to do it, you can skip that step. Just try to run k-means on the digit data and compute the adjusted run score. That's a good first step. And if you have the motivation or the Matplotlib familiarity, you can also do the visualization.
But it works.
Okay, so if we load the solutions, so we have this one. Oops. Probably we need to load the data first. So yeah, we need to load the data. So we need to load the data. So we load the digits. And then from the digits, we can already start to create a clustering, saying that we have 10 clusters. And then we want to predict the clusters from the data. So we fit and predict from the data. And then here we can find out what's the shape of our cluster. And now we have a 10 by 64 because we'll have our 10 images, okay? And 64 will be because we have the 8 by 8 pixel in a vectorized way, okay? So now what we can do is to actually visualize those. So that's what is this part here, to visualize the cluster. So as cluster centers, yes, the centroids, okay, the centroids of the cluster. So here we go for the 10 centroids. We create the subplots, and we go over the subplots, and we just show the ith centroids which we reshape by an 8 by 8 image. So is what we obtain. So for instance, the first centroid looked like a 4, this one looked like a 1, this one looked like a 9, 0, 6, 2, 3, 1, 7, maybe 7-ish, and 5. So somehow it seems that the centroid at least have a meaning, are meaningful when k-means find them.
Which digit is missing here? 8. And actually this one might be a mix of 1 and 8.
Yeah, because 1 is here and this is...
Yeah, because sometimes 1 has this shape and sometimes it's just a straight line.
Yeah, and the 8 is sometimes also without, not very well.
So yeah, so what I was saying is that the 8 is missing, and you see that here we have a 1 with this part of the 1, and sometimes some of the ones, they are just a straight line without this tiny bit, and in that case they tend to overlap with the 8. So it didn't find the concept of a pure 8 and a pure 1. It found two kinds of 1s, and one of them is mixed with the concept of 8. And it's kind of expected because k-means is not supervised, so there is no constraint to enforce that the centroid should match the true labels.
So then the second part here is to try to visualize into a 2D axis, like what we did with PCA before. But instead to do it with a PCA, we just use isomap, which is also a kind of decompositions using manifold, and plots on those two axes to see if we can see the different groups. So, and then we have like the different numbers on the training and the testing, I assume, or not?
No, it's the true labels and
the true label, okay.
cluster labels. So
Yes.
the first one, this is the colors match the cluster labels, and those match the digit class information. And you see that for most of them, it's actually correct.
The shape
this
is.
yellow here, it's approximately this blue here, this green here is approximately this. So we can actually compute the adjusted run score that is not part of the solution for some reason. Just compute it. You compare clusters score and then digits target. Digits target. So it's quite good because it's 67 on a range between 0 and 1. Actually, yes, it's expected to be close to 0 for random cluster assignments and close to 1 for perfect permutation. So
it's better than random.
It's significantly better than random. So yeah, it means that the structure of the pixel is actually matching quite well the labels that a human would put for this. So it's a good encoding.
I think I'm missing something about this one. So I get the idea that there's 10 different kinds of digits. And so
Yes.
your clusters are 10 because you're finding 10 kinds of things.
Groups, yes.
And I was able to get to the number that you just showed, but I'm not sure I get, so we're using the data, not the image. Is it just like image data into vectors?
Yeah.
And so how does it know, like it's not matching a data point into a cluster, it's matching an array into a cluster?
Yes. So so the original data for here we represent it in 2D, but we take the same pixel and we put them aligned in 64 values, and then it will compute distance between two vectors to see if they are in the same cluster or not. So they are, for instance, if I want to compute the distance between this one and this one, I will compute the distance between this pixel and this pixel. They are white, so it's going to be 0 minus 0 equals 0, plus the distance between this one and this one. And I do that every time. And then this one is matched to this one. So they are shaped as vector, but the pixels, they are always in the same order, so we can compute the distances. But compared to, so we treat the pixel as vectors. We ignore the 2D, the two-dimensional arrangement between the pixels. So it means that if we do a slight shift, that we will destroy everything. And if we have a high-resolution image that is not 8 by 8, that might not work very well anymore. So if we want to have this kind of translation invariance and stuff like that, and 2D small perturbations, then we would need something that is not just vectors of pixels, but maybe have some kind of preprocessing that extract patches and slide the patches or something like that, or use a convolutional neural network if you do your neural network. But for low resolution images, this is enough to treat that as vectors of pixel, and that should work.
Okay, and the pictures that are below, what are those pictures of?
So this is a projection in 2D using the isomap manifold learning system, which is some kind of nonlinear PCA. I don't remember exactly the mathematical definition.
Represents one digit?
Yeah, 1 point here is 1 digit. And here, those are the cluster labels, and here, those are the true labels. So here, all the purples here, they are maybe the ones or the zeros, and all are the ones, and so on.
Right, so two that look overlap, like the 1 and the 8, might be close together and overlapped in this picture? You can't distinguish them as easily?
Yeah, but because we project to 2D and originally it's 64D, there is some overlap that is just caused by the projection. And so even if the clustering algorithm is able to find good distinction, like for instance, this one that is in the middle, it's from this group here. Actually, in that case, it doesn't match, but
Right, but there's some that are pretty well.
yeah, for instance, this one, which is closer like here, is actually from the same label here. And you see that it's correctly assigned to the core group.
But it's not close to the bottom of the graph, right? So there's some that will be very distinguishable and some that will be not very distinguishable.
Yeah, so the fact that we are using a 2D visualization might induce some. So you should not focus too much on the spatial relationship. It's just a way to spread to see the grouping, and we can see that the grouping, they kind of match. Most of them, you have a permutation of the colors. The colors, they don't mean the same meaning in the two plots, but the groupings, they are approximately the same. And when we compute the adjusted run score, we see that it's a good clustering. So it's stable. Okay.
It's fine. Any other questions? So, okay, you can go.
So the next notebook is just some kind of summary of the API concept that we've introduced so far. So for all scikit-learn estimators, all the classes in scikit-learn that we can train on some data, they all have a fit method that will take either X alone if it's unsupervised, or X and Y if it's a supervised model. And in that case, Y is the labels or the target variables, and X is the feature matrix. So X most of the time is expected to be a two-dimensional array for the training data. And then we have additional methods that depends whether or not we are doing supervised classification or regression, or if we are doing unsupervised learning. So first, for supervised estimators, we have a predict method that will try to predict from a given X the expected value for Y. So here we pass a new X, and we will have a Y prediction. And the data types of the Y array that is returned by predict depends whether we are doing classification or regression. If it's classification, it is going to output integer labels. If it's for regression, it's going to predict continuous values, floating point values. For classifiers, sometimes some of the classifiers in scikit-learn, they have a natural probabilistic interpretation. Like for instance, logistic regression can give you some kind of confidence level normalized between 0 and 1. For each of the data points that on which you are making a prediction, if you are doing binary classification, for instance, the output is spam versus not spam, it can give you a prediction probability whether it's, for instance, 0.9 probability that it's spam and 0.1 probability that it's not spam, and the two probabilities should sum to 1. You can also do multi-class classification. For instance, you could classify the language of a text document out of 60 possible languages, for instance. And in that case, predict proba will return you an array with the first dimension is the number of text documents that you're trying to classify. And the second dimension is going to be the probabilities for each of the possible languages. And if you do the sum along that second dimension, the probabilities should sum to 1. Sometimes the classification model does not give you a confidence value that is normalized between 0 and 1, so you cannot directly interpret it as a probability, but it can still give you some kind of strength in the confidence. And this is usually done by the decision function method that will give you a value that is either positive if it's likely that it's a part of a specific class, or negative if it's not likely that it's part of a specific class, and close to 0 if it's not sure whether or not it's part of the class. And a very strong value will be, you can rank the predictions basically based on the decision function, but they are not normalized between 0 and 1. It's between minus infinity and plus infinity, and 0 is the boundary. Whereas here for predict proba, it's between 0 and 1, and 0.5 is the default threshold. Then you have this score function that takes, for supervised model, it takes a X and a Y, and will return a scoring metric by default. For classification, the default scoring metric is accuracy. For regression model is the coefficient of determination, R square coefficient. And for some estimator, you can also specify what kind of metrics that you want to return. We'll see examples later. And also some of the models, even if they are supervised, they can also transform the data. There are very few examples of that. But some of them, they can also have a natural internal representation of the data that they compute when they make their prediction, and it can be useful to introspect it. However, the transform method is mostly useful for unsupervised estimator, like PCA, for instance, or the scalars, the standard scalar, and so on. They are used to find a neural representation of the data that can be useful either for visualization or for introspection by humans and see what kind of structure we found in the data, or also for a pre-processing step for a supervised model. So when you have the transform method, usually, you also have the fit transform method, because you have fit, and sometimes it's more efficient to do fit and transform at the same time than calling fit followed by transform. For clustering algorithm, we also have the predict, but it's different than the one here, because the labels that are returned by the clustering algorithm, they don't have an absolute meaning. It's just the integers that are returned are just used to group the samples, to build groups, but they don't mean anything intrinsically. And some unsupervised models, they also do density estimation, so they can give you the likelihood that a data point is follow the structure of the model. So this can be useful. In this case, for instance, for Gaussian mixture models, that can be seen as a soft clustering algorithm, but it's also a density estimation model. And this is interesting because then you can use that, for instance, for anomaly detection. It's a way to do anomaly detection. And then we have a score function that depends on the models. Score for density estimation models or GMMs could be the aggregate log likelihood, the sum of the log likelihood of the full test set, and that can be used for selecting whether or not a hyperparameter is better than another one, like we would do for the supervised model. But here, a score takes a single argument, which is just X test and no Y test, because it's unsupervised. As a summary for the predict method, it can be used for classification, for regression, and for clustering. So those two are supervised. This one is unsupervised. Classification returns integers, whereas regression returns floating point values, and clustering returns also integers because it's a kind of unsupervised classification, basically. For transform, it really depends on the kind of algorithm. It can be used for preprocessing, for scaling. It can be used for dimensionality reduction, like we did with PCA, for instance. Or it can be used for feature extraction. PCA is also some kind of feature extraction, but there are other examples that we will see later, like for text feature extraction, for instance. And finally, there is also automated statistical ways to detect whether a feature is informative or not, for a specific supervised classification problem, for instance. And then we have some transformers that are supervised, and for feature selection, for instance, it can be very useful. And we also have examples in the coming notebooks. Okay. Question? Yeah.
Can you specify your own function for the model score?
By default, the classifiers, they will all have accuracy, but what you can do is, instead of calling score here, you call one of the functions from a scikit-learn matrix on the predictions. For instance, we did it earlier with a mean squared error or for accuracy. So you're not forced to use this score. For other models, like we will see later for model selection, for grid search, for instance, then you can pass to the grid search object the kind of score that you want to use to select the best model. Okay. So now we have a case study. So it's notebook number 10, where we're actually going to use some real data, some real features. So, and to do that, so we will introduce the concept of feature extraction or feature engineering. So there are mostly two kinds of features when we do machine learning. The most common or direct kind of features that we can use is the numerical features. And if you only have numerical features, then you can put them in a two-dimensional array with the first axis going to be the number of samples, the second axis is going to be the number of features. And this is already the case with the iris dataset. And here we have 4 features which are sepal length, sepal width, petal length, and petal width. And those are all in centimeters. So they are directly numerical features so that we can directly use them to fit machine learning models. It was also the case for all the images, like the digits, we had the gray level values for the pixels. Those are also naturally numerical features, so we can use them directly for machine learning. There are other kinds of features that are categorical. For instance, if you have a descriptor for an object, and you can have 3 kinds of colors for a product, for instance, red, blue, or purple. In that case, we will need to convert that to some kind of numerical representation to be able to fit that to logistic regression, for instance, because logistic regression is taking linear combinations of the feature values. So the feature values need to be numerical values, otherwise we cannot do the mathematics, the arithmetic operations. So what we could do is say that red is 0, blue is 1, and purple is 2. But then it's a problem. In your opinion, why is it a problem to assign some kind of arbitrary integer values to categorical variables like this? Yeah, so when you give integers, you have a natural ordering of the integer, but that ordering might not reflect something that exists in the original data. For instance, if you say that 0 is red, 1 is blue, and purple is 2, it means that purple and blue are very close to one another, and blue and red are close to one another, and red and purple are not as close to one another, which is wrong. There is no, it doesn't really reflect the colors of the product. So if we do that, we introduce a bias in the data that comes from nowhere. It's completely arbitrary, and that might lead the model to make bad predictions, basically. So in general, for many machine learning algorithms, we will, instead of taking integer values for the colors, we will take the color features, the color column, and extract 3 different columns. One which will be color equals purple, true or false. Color equals blue, true or false. And colors equal red, true or false. If it's true, we set it to 1, so it's numerical value. If it's false, we set it to 0. And we will expect that there is only one of them that will be set to true and all the others set to false. And in that case, we have some kind of natural metric space that will reflect the distances between the color without introducing a bias, basically. If it's the same color, it has a distance of 0 for those features. If it's a different color, it has a distance of 1, or square root of 2, or I don't know. Anyway. So if we do this kind of encoding of the categorical variable, then we can concatenate it to the numerical variable, and we have done the feature engineering, basically. So this kind of transformation for the categorical variable is what we call one-hot encoding, because only one of them is expected to be hot, set to 1, and the other are expected to be cold, set to 0. So one-hot encoding is transforming a categorical variable with n possible values into n numerical variables with 0 and 1 as values. Okay? So here we took the example of the iris dataset where we treat the target variable as an input feature and a categorical variable. It's possible to do that. But here we have another dataset where the records are actually recorded as a dictionary. So we have a dictionary with 2 keys. The first key is the city name, and the second key is the temperature. The temperature value is a continuous variable, so a floating point number. But the city variable is a categorical variable that has a finite number of possible values. Those are the cities in the world. So Dubai, London, and San Francisco. Sorry? A question? No? Okay. So if we define those measurements, then we can convert that as a numerical feature matrix by using what we call the dict vectorizer in scikit-learn. So dict vectorizer will return a SciPy sparse matrix, but that we can convert to an NumPy array just for visualization purpose. So if we do that, then you see that the CT variable has been encoded, one-hot encoded into 3 variables, and the temperature variable has been just stuck as a single column and concatenated. And if you look at the get feature names, you see that what is the meaning of those numerical values. So the dict vectorizer is doing already, if your original data, you can load it from a database, for instance, return this kind of data structure, then it's very easy to use that to do the feature engineering in one step. Sometimes it's more complicated to do. And also sometimes you want to derive features by combining several features together, as we did with PCA previously. So it's also possible to do that. Sometimes we have original data that has very noisy columns, and we might want to use some of the columns, ignore others, fill missing values, convert the categorical variables into numerical variables using one-hot encoding. And if you have this kind of problem, typically the original data format that is very common is CSV file format, which is very bad. It's the way it is. A better file format for this kind of structured columnar data is called Parquet, which is very efficient if you have columns with different types, like timestamp, text variable for categorical value, numerical values in different columns with different precision levels. Then you could use the Parquet file format, and Pandas is also able to load this kind of file format. And then you can use Pandas to do the feature engineering, convert that into some kind of numerical NumPy array, and then use that resulting feature engineering to feed the scikit-learn model. So here, if we load this file format, this CSV file that is downloaded in the dataset folder, then you can have a look at the column names, because Pandas is automatically reading the first line of the CSV file and interpreting that as the column names. And you see that we have the passenger class, a column that is a Boolean value, whether or not the passenger has survived the Titanic event. The name of the passenger, the sex, the age, so this is a numerical variable. Whether or not there were siblings or spouses in the ship as passengers. P-arch, I don't remember what it means. A number of parents and children aboard. Ticket is the ticket number. Why not? The fare, the price that they paid, the cabin number. The city the port where they embarked. I think there are 3 ports: Cherbourg, Queenstown, and Southampton. Boat is whether they were close to a lifeboat. Maybe I'm not sure. Body identification number, so it's a unique number, and destination, the home and destination encoded as a single string. So you can see that some of those variables are useful as predictive features, but others are not useful at all. So here, for instance, we might want to build a classification model that will predict whether or not a passenger is going to survive the Titanic or not based on the other attributes. So in your opinion, which attribute is not informative at all?
Ticket number.
The ticket number. Why? Who said?
It's probably just
It-
number. I mean, there is class and passenger fare, which is
Yeah.
indicative of whether the
Yeah.
class they are.
So it's likely that the ticket number is a unique value. So if it's unique for each individual passenger, there is no redundancy. So we are not able to do any kind of statistical structure extraction from unique values. Unless the ticket number is structured in a specific way, but then we might not want to use that. But if we need to do some kind of feature engineering to extract the several components of the feature number, of the number. And in your opinion, what feature can be very informative? The sex, age, body number. I think this is also a unique identification number, but it might be only 0. Yeah, it might be -1 if they survived. So, but maybe they didn't find the body, and in that case, it's also missing. I don't know. So, sex and age. Why is it the case that it might be informative? Yeah, because women and children were apparently given the priority to enter the lifeboats, and so didn't die by drowning in cold water. But it's not the case for all of them. And also, another one that maybe that is apparently very important is the class, the passenger class. Do you know why? Because the first class were at the top of the boat and very close to the lifeboat, where the third class passengers were at the very bottom, and they had to take a lot of time to reach the lifeboats, basically. And so it was too late, and because there were too few lifeboats. And we will see if the model are able to capture this kind of historical stuff that we know about the Titanic. So when we load the data in a data frame, we can use Titanic head. So this is a function of pandas data frame. And the pandas data frame structure is very useful in this case because it has a natural way to represent heterogeneously typed columns, basically. NumPy array is very good when everything has the same data type. It's possible to use NumPy array with different types or different columns, but it's really cumbersome. So if you have different types or different columns, use pandas to do the pre-processing. So here you see that some of the columns have string values, like the names. Other are string values, but with 2 possible values. Where here there are unique values. Basically, the names are approximately unique. And other columns are naturally numerical data. So what we can do is extract the survived column as the target variable, and those columns as the features that we want to use for prediction. So let's have a look at the features. We will just focus on those. So the port of embarkment, the fare, so most of them are numerical, but there is sex, which is categorical, and embarked, which is also categorical. It can be Southampton, Queenstown, and Cherbourg. So for the categorical variable, we need to do the one-hot encoding. So in pandas, it's possible to use getDummies to do that. And it will do that automatically. So you see now that we have sex male and sex females. Those are 2 columns that come from this single column, basically. And we have the same for embarked here, the 3 columns. Okay, so now that we have this, we have only numerical features, and we can do machine learning. We can call Scikit-learn on that data. So what's the point of this part? Okay, it's just to focus on the getDummies stuff. I don't see the difference. It's just that we store the results, basically. Okay. So it's the same operation, but this time we store the result, and we will use that for machine learning. So you can, in a pandas data frame, if it's only numerical value, you can call the values attribute, and then what you get as a result is a NumPy array. And here you see that the data type is floating point values. If you still add string values or categorical variables here, the data type would be object, and in that case, Scikit-learn will reject that because it's not valid input. However, you can also see that there are still entries that are set to none, which means not a number. And sometimes none, it's the case here for this column, age, it's a missing value. It can be used to encode the fact that we don't know what was the age of that person. It wasn't recorded. So in pandas, NaN are naturally used to parse CSV file with empty missing values. So many machine learning algorithms will not naturally deal with NaNs. So you need to find a way to fill the NaNs with some arbitrary placeholder value that will be neutral in some respect. So in Scikit-learn, what you can do is use this imputer preprocessing to get rid of the NaNs. And basically, it will replace the missing values by the median age or the average age so that it's kind of neutral. And there might be more advanced ways to deal with NaNs, but this is some kind of way to deal with it when it's a numerical value. So here we do a train test split, and then we fit an imputer on the training data, and then we transform the train and test data to replace the missing values with the statistics that were computed in the training data. So it's a bit like the scaling, but this time the statistics are used to do the feature imputation for the missing values. So here again, we only do it, we find it on the train data, and then we transform both the training and the test data with the same imputer. So once we have done this, you can see that we don't have any missing values anymore. So this has been recorded in train data finite. Once we have this with this model, a good practice is to try one of the dummy classifiers of Scikit-learn, or the dummy models. Those are baseline models that give you they are very fast to train. And basically, the dummy classifier with the strategy, which is called most frequent, will ignore the input data and just focus on the target variable and output the most frequent class for the target variable, which is in this case not survived. I think the majority of the people died. And so if you do that, you will have a 63% accuracy already, because the two classes are not balanced. So using the dummy classifier is actually give you something that is higher than 0.5. So here there is an example, an exercise, which is actually, instead of using the dummy classifier to train a real machine learning algorithm, you can try a logistic regression or a random forest classifier. And you can train and compute the score on the test data. And what you can do also is to try to remove some features and see if it can improve the test score. Okay? So you can import random forest classifier. I think we've never imported it so far. It's from sklearn.ensemble. Import random forest classifier. Okay. And if you don't know what parameters, you can use the default parameters, but you can also have a look at the documentation to know what is the meaning of the different parameters, n estimators, criterion, and so on. So you can play a bit with those values to change those values and see if it can improve the model. Okay. So let's do this. 5 minutes. A question? Yes. So the question is, do we need to rescale the data? That's actually a good question, and you can answer by trying. The answer is that for random forest classifier, it won't change much, because the decision trees algorithm are naturally approximately scale invariant. But for logistic regression, it's a very good point. Like for linear models, it generally helps a bit to scale correctly the data so that they are approximately on the same scale. And for nearest neighbors classifier, it would be even more important. So the identifiers, we should not take them as features. So we should not scale them. But for all the other numerical values, that once we have done this feature engineering using the get dummies, we can scale. We could use min-max, for instance, min-max scalar. And for the categorical variable, it will not change because it could be a scale between 0 and 1, and so they should stay the same. But for the fare here, you see that this is a price in dollar. So you see that this is a very different scale, 0 and 1. So using min-max scalar is probably a good idea. And all the features here are positive values. So min-max scalar is a good guess, and there are no outliers. I think the age is approximately always the same. The price, there is no extreme values, so you can use a min-max scalar in that case, if you want to give it a try. Yes, another question.
What's the dummy classifier do besides just calculate the difference between two classes?
No, it's not even computing the difference between the two classes. It's counting the number of times it is survived and the number of times it is not survived, and it's predicting the majority class. So it's not even looking at the values of X, it just looks at the values of Y and find the class that is the most likely and always predict this one. So it's actually not that dummy, it's a smart baseline, but it's just a baseline. It's completely not looking at X. It's a constant classifier, basically. Okay. So let's have a look at the solution. So first, just to fit the model, we can use the default hyperparameters. So logistic regression without parameters, we train it on the full data and we compute the test set, the test score on the test set. We do the same with random forest classifier. Here, we typically the default value for n estimators in scikit-learn is too small, and we are going to change this default value in some point in the future. So you can increase it to 100 or 500. Typically, the higher the better, but at some point it's too expensive, and at some point you have diminishing returns. So just try some significantly, 100 for instance, and then you set it to 200, and you see if that improves the result. If it doesn't improve, go back to 100. Then we can also extract a subset of the features and do the same, do the imputation again, and do that. So basically, we do the same without the feature which was called embarked previously, and we do the same operations, and we will compare the results. So here you see that logistic regression is slightly better than random forest classification. And if we remove the embarked stuff, logistic regression is actually slightly below, and random forest is slightly better. So some features might be helpful or not, depending on the model. And maybe also here there is some random effect because we did a single trend test split. And maybe if we resample the data, we might have small variations. So maybe it's not that... we should not draw conclusions from that small experiment because the values are still very close. Actually, this is kind of a bit different, so that's weird. Let's try to see if we change the random state. Here, yeah. That's still a significant difference. Yeah, that's weird. I wouldn't have expected this. Okay, anyway. So here we did we use pandas to do the get dummies, which is actually a problem because then it's hard to basically do the imputation and the scaling. Like we didn't do any kind of scaling, but if we wanted to do a scaling operation, we would have to mix and match pandas operation with scaling operations. And furthermore, here we need to do the get dummies on the full data set before doing the train test split, which is actually cheating. And we should not do that. We should do the categorical feature encoding after the train test split. but with the Pandas API, it's not possible to do that easily. So actually, this is something that was improved recently in the master branch of Scikit-learn, and it's going to be part of the next release. Where is it? Here. There is a new class which is called column transformer that makes it possible to deal with mixed data types in the input. So here is an example from the Scikit-learn documentation on the development branch. So if you want to access it, you can go to scikit-learn.org/dev. And basically, this is the documentation for the master branch of Scikit-learn, so unreleased yet. And here we are also using the dataset from the Titanic. And we are also using Pandas to parse the CSV file. But then we are not using Pandas to do the categorical feature encoding. Instead, we are defining two scikit-learn pipelines for the numerical features, so age and fare, for instance, and for the categorical features embarked, sex, and P class, a passenger class, we are going to define another pipeline of operation. So this pipeline of operation for the numerical values is going to combine the simple imputer with the median for the numerical variables, then followed by the standard scalar. And then for the categorical variables, we do a simple imputer with a constant strategy that replaces all the nan by a missing label, so that it's still a string. And then once we have these new string values for the missing variables, we can use the one-hot encoder to convert that to the same kind of operation that getDummies would have done. And if there are unknown elements at the test time, we will just ignore them without any kind of warning. And once we have those two pipelines, we can combine them using the column transformer. And then we say the numerical features, we will apply the numerical transformer. For the categorical features, we will apply the categorical transformer. And all the other features that are not part of this subset, we will just drop them and ignore them, basically. And when you have this, then you can treat that as the feature engineering step, the preprocessing step. So it's a very complex preprocessing. And create a new pipeline that will sequentially combine the preprocessor and the classifier, logistic regression, for instance. And then we can do a train test split or cross-validation, and it will just do everything on the train set and then apply the transformation on the test set. And then we have the final score, which is correct, which is very similar to what we got in the tutorial. And then we can use grid search. This is something that we are going to introduce soon. Okay, so back to the tutorial. So I think we finished this notebook. So we can switch to the next one. But before, if there are any question on this? Nope. Okay. Okay, so I close this. Okay. So the next notebook, number 11, is text feature extraction. So here, so far, we've dealt with numerical features, naturally numerical features, and categorical variables. But there is another kind of data that can be used for classification, but cannot be directly used as such. We need to do some kind of transformation to be able to extract numerical features from those. And this is text documents. So the typical pipeline that we use for the classification of text document, or at least a good baseline, is what we call a bag of words encoding of text document. So assume that you have a text document that is a single sentence. This is how you get ends. The first step would be to split the white spaces, and extract all the different words and maybe apply some kind of normalization, like ignore the punctuation characters and put everything to lowercase or remove accents in some languages because they might not be consistent. Like in French, sometimes people do not type the accents. So you can normalize this by removing the accents if you want. And so this is the job of the tokenizer that will take a string of characters like this that represent the full document and will output a list of smaller strings for the individual tokens. A token can be a word, but a single word, but can be something else. And usually a token has been normalized. We have removed the casing information, for instance. So once we have this, we do this operation, this tokenizing operation for all the documents in the collection, in the training set. And then we record how many unique tokens we found in all the documents across the whole training set. And we will call that list of unique tokens the vocabulary. And so we can order those tokens by alphabetical order. And we will assign a specific dimension to each individual word. So if it's in alphabetical order, it starts with A. And so aardvark is going to be dimension 0. And Zist is going to be dimension 100,022, for instance, and so on. And once we have this, we will, if you have a new sentence, so if we have this sentence, for instance, it has the word get in it. The get will be mapped to a 1 in that dimension, in that space. And there is a 1 for ants. There is 0 for aardvark because the aardvark word is not part of that sentence. And so you see that this sentence here, after tokenization, has been mapped to that space because we have this vocabulary. So the vocabulary is the link between the token representation to the numerical representation. It's some kind of many hot encoding, basically, because we have several words per sentence. And so there can be several ones here, and all the words that do not occur in this specific document will be mapped to 0. So because the vocabulary is very large, it means that we can have 50,000 dimensions or 1 million dimensions. So something that is very large depends on the size of the data set and on the language and on the tokenizer also. Because of that, we will have many zeros in the encoded representation of the document, in the numerical representation of the document. So it's very important to use a sparse matrix. Typically, it's not possible to use a NumPy array in this case anymore, if you have a large document collection. So this is why Scikit-learn has several models that support working with sparse matrices. Typically, for text classification, it's a requirement. We cannot do otherwise. So here we have a small example with only a collection of only 2 documents. Those are 2 small sentences. Some say the world will end in fire, and the second second sentence, some say in ice. So if you take the length of the list X, it's 2 because there are 2 documents, and each of them has a different number of words or number of characters, but we don't care about that right now. So we just want to convert that list of text strings into a SciPy sparse matrix of bag of words encoding. So what we can do for that is use the countVectorizer class from Scikit-learn, and it will basically do all these operations that I've presented previously in one step. So when you go fit on that list of documents, it will call a tokenizer, build a vocabulary, assign each of the words to a specific dimension arbitrarily, and then you can use the vectorizer to transform the list of text documents to a SciPy sparse matrix. So here we have a sparse matrix with 2 rows and 9 columns. Why do we have 2 rows and why 9 columns?
The number of sentences is 2.
The number of sentences is 2, so this is the 2 rows. And why 9 columns?
There are 9 features with non-zero entries, right?
It's actually that there are 9 unique words across the documents. So for instance, here some and say are repeated twice in the document, so we ignore the repetition. But we say that some, say, the, word, and so on are part of the vocabulary that is common for all the documents. And so each of the vocabulary entries will be mapped to a specific dimension. So here the vocabulary size is 9, actually. We can check that. 9. So this is why we have 2 and 9 here. So when we print the sparse matrix, we have this representation that is not that informative. So it gives us the shape and it gives us the number of non-zero values. So it's interesting because we can see that it's already quite sparse even if we don't have that many documents. So because we have only 2 documents and 9 dimensions, we can convert it into a NumPy array. But for a realistic data set, we will not be able to do that. So here we have the first document that has been converted to this and the second document that has been converted to that. And we can get some interpretation by asking for the feature names, which is basically the vocabulary, to the vectorizer. And basically, the first dimension is end. Then we have fire, then we have ice, and it's missing from the first document. And what is also interesting is that we can do the inverse transformation on the bag of words representation back to the original token space. And here we see that the transformation was destructive because we did lose some information. We lose different kinds of information. Do you have an idea what did we lose in the operation? It's kind of obvious, but the order of the word, which is very important. And a tiny detail, the punctuation is not there anymore because it was stripped away by the tokenizer. And the casing information is also not there anymore. But the most important part is that we did lose the order information. And this is why we call that a bag of words, because in a bag, when you put stuff in a bag, you lose the order because you shake the bag and then you don't know the order of insertion anymore. And so the bag of word representation is just we record that we have seen this word, but we don't know in which context. Okay. So there is a variant of bag of words representation which is called TF-IDF vectorizer, which will basically scale and give weights instead of having 0 and 1 or 0, 2 if we see some words twice. We will have these positive values, but that have been scaled to values that can be larger than 1, but typically approximately all on the same scale. And actually what we are going to use for this scaling is the frequency of the word across documents, what we call the document frequency. So for instance, if you take the word the in English, like that's occurring here, it's a very frequent word, so it's not informative for many classification tasks. So we would like to decrease the weight of that word and naturally rescale that dimension so that it's not that important. And so this is what the TF-IDF vectorizer does naturally. It will compute the document frequencies and apply some mathematical rules using logarithms to downscale the words that are very frequent and upscale the words that are quite rare in comparatively. So if you want to see the exact definition of the mathematical transformation, you can use this notebook. You can also read the Wikipedia article on that. But beware that there are many variants of that TF-IDF normalization, and the one in Scikit-learn is not necessarily the one from Wikipedia, so you have to check the documentation of Scikit-learn, and there are parameters so that you can change it to something that is more standard. But we don't want to change it now because otherwise that might break the code for people. So it's historical choices. But in practice, the normalization that is done in Scikit-learn it works well. Like it doesn't change much if you change the parameters. Something that is more important actually is how we do the tokenization. If we want to preserve some information of the ordering, what we can do is instead of considering the individual tokens as dimensions, is take a sequence of 2 tokens and treat that as a dimension. So we will build artificial tokens that are actually the combinations of sequential tokens. So for instance, if you have this original sentence, this is how you get ends. The 1 gram representation would be extracting the individual tokens and treat that as individual dimensions. The bigram representation will be to extract this is how you get and get hence as tokens, basically. You see? And trigrams do the same for sequences of 3 elements, 3 words. So you can do also a combination of a unigram and bigram, for instance, and do the concatenation of the two and use that for your bag of words. And typically this is what we do. Like we take 1 gram and 2 grams of words, and this is very often a good representation. So that we keep some local information of the word ordering, but it's still fundamentally a bag of words. But sometimes you have words that have a very different meaning when they are concatenated with one another. For instance, if you take the word New York, if you tokenize it as new and York, you lose the information that it's New York City, for instance. Whereas if you keep the bigram, then you identify that you have the city of New York that has been mentioned. So to do n-gram extraction, you can use the n-gram range parameter of convectorizer of TF-IDF vectorizer. So let's do that with convectorizer. So you see now that in the vocabulary we have only bigrams, and so if we do that extraction, we have a different meaning for the bag of words. What we do often is, instead of using just bigrams, we use a mix of unigrams and bigrams, and this is what is called n-gram range, and we will extract from 1 to 2 gram information. So now in the vocabulary, we have the word and in, fire, ice, in fire, in ice, and so on. But only sequences of pairs of words that actually appear in the training set. And when you do that, you notice that then the dimensionality of the data is increasing very quickly. Okay? So if we take the same training set, there is another option in convectorizer which is called analyzer equal character. So if we use the character analyzer, which is an analyzer, it's basically a tokenizer plus some additional step. If we use the character analyzer instead of the word tokenizer, then we have a very different vocabulary. We have this as the feature names, the individual characters, and because we took bigrams, that's weird. Ah yes, there is a white space here. There are white spaces. Maybe we could even do that. Here we have the individual characters plus the bigrams and so on. So, in your opinion, when would that be useful to do this kind of feature extraction, to treat individual words? What kind of documents or kind of properties of documents we could better represent by using bigrams of character instead of considering the full words? Predict what?
States, the encoding of states.
The states?
Texting data, sometimes it's not like a full word, it's like TXT or...
Ah, okay. So a small... yes, but what kind of attribute of those kind of data would we like to predict? Might be... We could try to predict the next character. That's like if we want to do a smart keyboard. That's actually a good potential application of this. Another application for language. So this is what you said? Okay. Yeah, if you want to do language predictions, this is if you want the frequencies of sequences of 2 characters, or 3 characters, or 4 characters. You can very easily predict the language, especially when the language has a different alphabet, like in Arabic or Chinese or Japanese. Those are different characters than from Latin alphabets. But even for European languages, for instance, where they all have approximately the same alphabet, the frequencies of bigrams will be very different, and it will be very easy to use that to build a classifier to detect the language. And you can have a high accuracy with this. But however, if you want to predict the topic of a document, here you destroy most of the information. It's really, or if you want to do sentiment analysis, whether the document is positive or negative, this kind of representation is probably very bad. So here there is an exercise, which is to take the Zen of Python, by Tim Peters, which is this text that explains the spiritual definition of what is good in Python. And use the TF-IDF transformer. So you need to treat that as a set of documents, and you will basically split on the new line character. So you need to turn this big string into a list of strings, and then use the TF-IDF vectorizer to compute the TF and DF encoding of the data, and then use that to find the words that have the highest score. And you can also do that for bigrams if you want. So try to find in the columns the ones that have the highest average score or the total score. Okay? And see if it's informative with respect to the Zen of Python. Okay, that's 5 minutes. So let's see the solutions so that we can move forward. So, so first we need to build the collection of text document by splitting the lines. So we can use this. And then we will fit a different count vectorizer for different values of n to extract the n-grams. And for each of them, we will extract the transformation, and then we will sum across the documents to count the number of times we see different words. And then we will compute the argmax, which will find the most frequent word. Oops, sorry. For each of those cases, and because this is gonna give you an integer value of the column, the dimension of the specific column, then we will need to use the inverse vocabulary, which is accessible using get feature names, to find the string representation of the most common word based on that vectorizer. I don't know why this is doing this. Okay. And then we can do the same with the TF-IDF vectorizer, and we can normalize or not using the L2 norm, and we'll see what kind of impact it has. I forgot to execute this. Okay. So if you extract bigrams using count vectorizer, the most frequent bigram is better than. The most frequent trigram is better than, and the most frequent fourgram is if the implementation is. Let's have a look at this. And you see that is better is very frequent, because there is better everywhere. But for fourgrams, it's very rare to have repeated fourgrams, and there is only those two here that are repeated. Okay? Then we do the same for the TF-IDF. And here, with L2 normalization, it's count, and otherwise it's special. It's really hard to understand what is the TF-IDF normalization is doing, and especially when you combine it with the L2 normalization. But you see that it's changing what is the most frequent word across the collection. So L2 norm, which means that when we do that, we will make sure that the result of the transformation, all the elements, they have the vector of the encoding is basically as norm1, whereas if we said norm equals none, it might be left to the result of the TF-IDF normalization by itself. So this is a second stage normalization that we have applied document by document. So in your opinion, why do we want to do a L2 normalization for document representation? Why would it be useful for which kind of application? It would be useful to normalize the coefficients, the extracted features for a document using the L2 norm, document by document. It can be done for count vectorizer or for TF vectorizer. For both of them, you could normalize. basically the answer is that if we normalize, we will basically make sure that a long document will be treated equally as a short document. Because if we don't normalize, a very long document will have a very long norm, and so that might impact the classifier. So for some applications like predicting the topic of a document, whether it's a sport, business, I don't know, technology, you don't really care about the length of the document. So normalizing by the length of the document is actually a good idea, because that makes the model invariant with respect to the length. So it's a good inductive bias that you give to the model. For other applications, for instance, if you want to predict the complexity of a document, then the length might be very important. So it might be a bad idea to do this kind of normalization. So it really depends on the application. So speaking of application, the next notebook is putting this kind of feature extraction in practice by doing a spam detector for SMS messages. So here is the one of the standard data sets where it's as an input we have a list of short text documents, and as the output we have a binary value y, which is 1 if it's a spam message and 0 if it's a ham or a non-spam message, something that is a regular document, or a regular valid legit message represents. Okay. So this dataset should have been downloaded already if you run this command, fetch data. And it should be in that folder, dataset SMS spam collection. We can open the file and split the tabs. So this is a special sign for tabulations. And basically the document have been already tokenized, and they use this tab separator for the tokens. And each of the line in that text file is a specific message, SMS message. So we just use that. And also the first, no, actually I'm speaking, yeah. There is only a single tab which is separating the label from the text document. Okay. So before the tab we have the label, whether it's spam or not spam. And after the tab we have the actual text document, the sentence basically. So let's have a look. So here the first sentence is this one. The first message is this one. Go until drawing point crazy, available only in bugs anyway. And if we look at the values of y for the first 10 documents, we see that the first 2 documents are 0, which means they are legit messages, and the third one is a spam message. So let's have a look at the third one. So this is the first one, second one, third one. And you see free entry in a 2-weekly competition to win FA Cup final or whatever. So typically we have when you have the word free, win and stuff like that, it looks like a spam. So we will see if we can train a classifier to detect those kind of spam messages automatically from the labels that we have. So we can first, what's wrong with this? NP, I didn't import NumPy. Okay. First, it's a good idea to compute the relative frequency of the 2 classes. So because we're using positive integers, we can use a NumPy bin count to do so, which is very efficient. And so you can see that most of the document, the vast majority of the document, are non-spam, they are regular messages. But a small fraction of them, they are the spam documents. So what we can do is actually see the fraction by doing, because y has a value between 0 and 1, if we take np min of y, we will see the fraction of spam messages, and those are 13% of the messages are spam. Here you see that y is a list because we didn't convert it into an NumPy array, and even for the text it's the list of strings. So we will need to do some transformation for that. The train test split function from scikit-learn, it works on lists. It also works on NumPy arrays, but it can also accept lists, and it will do the same kind of permutation as previously. So if I do this, make it more visible. Okay. So, sorry. Clicked at a bad location. Okay. So here we do the train test split as usual, but this time on the list of text document and on the labels. And we keep 25% for the test set. And we make sure that we respect the stratification so that the balancing of the two classes is preserved in the train and the test split. Okay? Then we will use the count vectorizer as previously with the default attributes. So you can see that by default it's focusing on words. There are many attributes, and there is also the regular expression that is being used by the tokenizer to identify words. If you want to customize that, you can. You can also pass a predefined vocabulary, otherwise it will extract it automatically from the training set. So let's do that. We fit on the training set. Again, it's not defined. Forgot to execute this cell. Okay. So we fit on the training set, and then we transform both the training set and the test set into SciPy sparse matrices. So this time the vocabulary is significantly larger than previously, but it's still not that big because the data set is not too big. And then the training set have been transformed this way. So this is the number of documents, and this is the number of unique words in the training set. And each unique word has been assigned a specific dimension according to the vocabulary. So we can have a look at the feature names. The feature names are organized by alphabetical order. So if we take the first 20 elements, we see many numerical codes because the numerical values are at the beginning in the alphabetical order. But if we have a look at 20 words in the middle of this, you can see stuff that start with a C, and those are regular English words, so that looks fine. Those might be treated as noise if they are very rare, but sometimes they can be repeated and they can be actually useful. Some of them might be codes for spams, actually, so it might be interesting to identify them as markers. So the test set has 4,000 documents, and the train set has 4,000 documents, a bit more, and the test set is 25%. So we have this, and you see that they share the same vocabulary because we use the same vocabularizer, the same count vectorizer, to transform the documents from the train and test set in the same way. And this is very important to reuse the same vectorizer. If you use a different vectorizer that you train only on the test set, you will have completely random predictions. So now that we have this, we can actually train a machine learning model, so logistic regression. It's using also the default parameters, the hyperparameters. You can read the documentation as usual if you want to learn more about what they mean. But in Scikit-learn, we try to give reasonably good default values. There is no guarantee that they are optimal, but they should not completely fail either. So let's try to fit the model and then compute the score. And you see that here we already have 80% accuracy on the test set. Is it a good score or a bad score? It's good. If we had a completely random model or baseline model, what would be the accuracy? The baseline, because the classes are not balanced, would be to always predict not spam. And we would, because there are 13% of values that are not spam, like a very baseline model that ignores the text and just predict a constant not spam output, would have an accuracy of 87 approximately. So it's still significantly better than that. But you see that the baseline is already has a high accuracy. So maybe we should not use the accuracy to quantify the model, but something like the precision or F1 score or the ROC AUC. But we will see that later in another notebook. We can also have a look at the training set, and we see that the score on the training set is slightly better. It's not perfect, but it's slightly better. And with the gap between the two is actually what we call the overfitting. And in this case, there is not too much overfitting. So it's good. Because we have a linear model, we can have a look at the coef attribute of the model here. Once we have fitted the model, we give weights to each individual words, each individual dimension which map to a word, and the absolute value of that coefficient might give you the strength of the word, and the sign might be indicative of whether or not it's a spam or not a spam. So what we can do is look at the top coefficients, the top positive coefficients, and the top negative coefficients. And for each of those coefficients, look at the feature names, which is done here. Where are the feature names? Yeah, here we look at the feature names of the interesting coefficients. And we will use matplotlib to do like a graphical summary of the most important coefficients. So this is it. So maybe it's a bit too small, but if you do it on your screen, you can read the names here. And so you see that for spam values, the strongest words are those. So there is TXT, UK. So this is a bit weird. Maybe TXT might be informative, but UK, maybe it's a bias of the training set, because I think it was collected in the UK, and maybe the spam in the UK they have URLs with the .uk at the end, co.uk or something like that. But maybe in a different dataset that might not be the same. However, ringtone is likely to be very much a spam marker. And here you can also see price, cost, free, mobile, service, claim, won, you won. This kind of stuff, they are like really strong markers. And call 925, whatever, to get your price. Those are really strong markers of spam. Here you have negative stuff. So this is a bit weird, like GT, I don't know why. We would have to look at specific sentences of those occurrences to know what those tokens mean. But something that you can see that the strongest value here is -1, and the biggest value here is +2. So actually, the spam marker, they have an absolute value that is significantly larger than the negative coefficients. We can also use this min df equals 2, which will basically trim the dimensions where we have unique words that are not repeated at least twice. So that if a word is too rare, we remove it from the vocabulary because it's likely to not be informative. And we can do that and see the accuracy on the train and test. And maybe it's slightly better. I don't remember. 1949, and this is actually not better. What else did we change? I don't remember. Vectorizer, we use the default values. So in this case, apparently this is not significantly better. We can also use maxdf equals 0.9, for instance. So that will remove words that are present more than 90% of the time. And this we can maybe remove stronger words that are very rare. That will reduce the dimension. It doesn't change much. But here the model is working on a smaller set of features, so it might be faster to predict, so that might still be a good thing to do. And we could just try something lower, like 0.8. It's still approximately the same. That doesn't change much. We can also change the regularization parameter of this guy, and it doesn't change anything. So those scores are very stable, apparently. So the feature names, the size of the vocabulary has shrunk by quite a bit here because I've used this to basically trim some stuff that were not informative. words that are either too rare or too frequent, they are likely to be not informative, so we can remove them. And we can have a look at the feature names. I don't know why we do that. And again, the feature coefficient after we did that change in the vectorizer. And we still see stuff like ringtone, sexy now is the first one, girls. Yeah, it's different kind of spam that were highlighted by this model, but I'm sure that we would find the same word just in a different order. So what is interesting here is that if you recap from this morning, I had this approximately is diagram, and you see that here we are going from the text representation to the fictor vectors using the vectorizer fit transform. Fit transform is extracting the vocabulary and then doing the transformation, and then we keep this vec object for later so that we can apply the same transformation on the new text document. This is very important. And then to do the actual classification algorithm, we will use a logistic regression and we will fit on the feature vectors. And then we will get the CLF is modified in place and it's actually the predictive model. And then we can call predict to make the prediction. So this is how the Scikit-learn API maps to this generic data flow. So here there is an exercise which is actually to use TF-IDF. I think it's more interesting to see the next notebook. So I think we can skip this. We can just have a look at the result. And in this case, TF-IDF is not better than Count Vectorizer. However, what is very interesting is to use MinDF and ngrams, and that might improve the quality. Let's check. So you see, if we use TF-IDF, the quality is actually worse than before. We still have ringtone, free, call, stop, claim, whatever. Those are the spam words. They are approximately the same, maybe in a slightly different order. And here, if we extract n-grams of words, and we remove the n-grams that are less than 10 times so that we don't explode the number of dimensions, that might improve a bit. Actually, we didn't compute the, the scores. I will take the scores here. Actually, it's still the same, or approximately the same. So, but we use a TF-IDF vectorizer, so let's use Count Vectorizer. You see that it's slightly better. So using bigrams, it's very often the case that it's actually useful, and we can have a look at the bigrams. Here, yeah, there is you have, and probably you have one if we have extracted trigrams would have shown up. For the important spam words, we see unigrams, but here you can see that there are 1, 2 for those are like connection words or connection expression that are indicative of non-spam stuff, apparently and statistically. Okay. So let's move to the next one, which is actually a very important one, which is called cross-validation. Maybe it's going to be the last one that we have time to do. So cross-validation and scoring methods. So this is notebook number 13. So up until now, to do the evaluation of the quality of the model, we did a single train test split. So we start from all labeled data, and we take the largest fraction of that for the training set, and a smaller fraction of that, like 25%, for instance, as the test data. However, the quality of the model, the quality of the performance metric that we can measure on the test data, because the test data might be small, might depend a lot of the randomness of the split. So if we change the random seed, we might have very different values, and so using this, a single split like that might be problematic because we might be misled into thinking that some model is better than another one, whereas the actual order would have changed if we had changed the order of the split or the randomness of the split. So instead of doing this, what we can do is iterate this procedure many times with different train test splits. And when we do this procedure of doing that many times sequentially, is what we call cross-validation. So the most natural, the traditional way to do cross-validation is what we call k-fold cross-validation. So sometimes we set, most of the time we would set k to 5 or 10. So if k is set to 5, we call that 5-fold cross-validation. And basically we will split the full training set into the 5-fold with equal size, approximately equal size. And each of the fold will be considered as the test set. And all the 4 other folds, the green ones, will be concatenated to create the train set. And so we will have 5 different splits where each of the folds will be used as the test set sequentially. And so we will basically train 5 different models independently of one another on those 5 variations of the data set. And for each of those models, we will compute a performance metric, and then we can take the average across the 5-fold to have something that is more stable and less dependent on a specific train test split, basically. So we can do this using the iris dataset and the k-neighbors classifier. Those are baseline benchmarks, basically. So if we have a look at Y in the iris dataset, you see that the data has been ordered by the class information. So that might be actually misleading, because if we do a split, 5-fold split, we will have all the 0 in the same fold, and that might be a problem. So instead, we will use NumPy to do a permutation, a random permutation of the samples, and we can do that using X permutation and Y permutation and reassign that. Here you see Y has been randomly permutated, and we apply the same permutation to X. So when we do train test split, it does that automatically internally. There is also another utility function in Scikit-learn which is called shuffle that does also the same step. But if you are dealing with NumPy arrays, it's very easy to use a NumPy permutation to do that automatically. So if we want to implement 5-fold cross-validation manually, assuming that we have done a random permutation first, then we can do this. So we define k equals 5. We measure the number of samples. We will define the fold size as the number of samples divided using the Euclidean division by 5-fold. And then we will define a list of scores that we will aggregate and a list of masks for the test set. So what we call the test mask is going to be a mask of zeros, except of a range of values between the fold index multiplied by the fold size. So we are going to set to true the range of samples that are going to be used for the test set. And all the other values that are set to false will be used for the training set. So let's do this. And you see that then we use the test mask to extract the test set, and the negative of the test mask to extract the training set. And then we fit the classifier on the training set, and we compute the score on the test set as usual. And we collect all the scores and all the masks. So let's do this. And what we can do is then use matplotlib matcho to see the mask information. So here might be a bit small, but here the lines in that matrix are 0, 1, 2, 3, 4. So those are the 5 possible values for k, so the different folds. And you see those are the ranges of samples. We have 150 samples in the full training set. For the first fold, for the first split, we will take the first fold as the validation set, and all the white samples here for the training set. On the second line, we will use that for the validation set, and all the whites are concatenated for the training set, and so on. And we will train the 5 models independently and compute the scores and aggregate the scores. So here are the scores. So you see on the first split, it's 96, 97, then 90%, then 100%, 100%, and 93%. So you see that there is a significant variability across the different splits. But then if we take the average should be much more stable than the individual split. Okay? So in scikit-learn, we have this utility function which is called cross-val score for the model selection package. And you just give it the classifier and the full training set, and it will do that automatically for you. So you don't have to write this loop. It's doing that automatically internally for you. But it's good to know how it works so that it's not magic. But then you should get some similar results. Actually, here you see that by default we have only 3 folds, because this is the default value of scikit-learn right now. It's actually a bad default value. We should increase it to 5 as the default. But if we set to 5, then we have something similar to the previous iteration. In your opinion, why it's interesting to have to use 3-fold cross-validation, and why it can be sometimes better to use 5-fold cross-validation? What are the pros and cons of using a small or large value for the number of folds? Mm-hmm.
So if you get, if you try 3 and you get numbers that are similar, maybe you don't have to worry too much, but if you get numbers that are pretty highly varying, maybe you use more to make things more stable.
Yes. So actually, if you try 3, you have a higher likelihood to have numbers that are similar, but by chance. And actually, it's kind of counterintuitive, but it means that you might not necessarily see the actual variability of the data. So the standard deviation when you compute it on 3 elements might be artificially low by chance, basically. Whereas when you have 5, you might see more the confidence interval, basically, might be better. However, when you try 5, it's much more expensive because you have to fit 5 models. So if the data set is big, that might take more time than 3. So this is why we decided 3 in the beginning for scikit-learn, because it's less compute intensive. But in practice, it's still better to use 5. Another?
Is there ever any overlap between the groups? What does that mean if you have smaller groups?
So when we do 5-fold cross-validation, we should make sure that there is no overlap at all. Here you see the mask. They are either true and false. So for a specific split, either you are in the test set or in the train set. You cannot be gray. You are either black or white, and there is no sample that is both of them. Here you see that we selected different folds for different cross-validation split. We could have folds splits that would have partially been using the same, or maybe we could use only. I won't say the details. We will see later more examples. The second part of the question was, I don't remember.
If there's small data sets. So if you only have maybe 25, I know this one's small, but every time you're splitting,
Yeah.
putting it up 5 different groups, then if you have, sorry,
Yeah.
say vocabulary or whatever again, say for one of your cases, you only have a few samples that are standard.
Yeah. So if you have a very small data set and you use 5-fold cross-validation, then the test set is going to be very small, for instance. Or if you use 10-fold cross-validation, it's going to be even smaller. And that might be a problem because then you have a lot of variability, like computing the score on very few samples, so might be a problem. But you have range across many more splits, so all in all, it's not necessarily a big problem. What is more of a problem is that the fact that if you use 3-fold cross-validation, it means that you're going to use only 2/3 of the data as the training set. And when you have a small data set in the first place and you use an even smaller 2/3 instead of 4/5, for instance, that's very small, and the performance of the model tends to be much worse when you have a smaller training set. And so the estimate of the true validation error might be actually too pessimistic if you use CV equals 3. And so CV equals 5 tends to be a good trade-off between being pessimistic, being able to capture the variability. So in general, people would tend to use CV equals 5 to 10, but 10 is going to be more expensive because you have to do repeated experiments many more times.
Question.
Yes?
So what are we evaluating here? Are we evaluating the classifier itself, or are we evaluating how good of a model we have built?
So that's a very good question. Are we evaluating the classifier itself, or how good the modeling is? And that's actually not a specific classifier that we are evaluating, because here you can see that we have 5 different classifiers. Each of those classifiers are trained independently on different splits. So it's not one single classifier that we are evaluating. It's actually the choice of the features plus the choice of the classifier type plus the choice of the classifier hyperparameters. It's the actual full modeling pipeline that we are evaluating, all the parameters of the modeling pipeline. And we try to evaluate the ability of that pipeline to run correctly in future data that we haven't seen yet, and the choice of all those modeling decisions that we made. Yes, if you have other questions. Okay, so this was k-fold cross-validation, but there are actually variants. So in scalar model selection, you have actually classes like k-fold, stratified k-fold, and shuffle split, and there are many more. So let's have a look at those classes. So stratified k-fold with n split equals 5, and you see here that when we do a CV split on some data set, it will return train and test arrays, and those arrays are integer values that can be used to fancy index the training set. And so basically what is important here for stratified k-fold is that it will look at the target value of the classes, basically, to find splits that preserve the balancing of the classes when it does the split. So to make this more easy to understand, there is some visualization here. So here we do stratified shuffle split. And here you see we're using n and the number of split that is set to 5. And so here you see that for the first split, it used for the test set a concatenation of samples from 0 to 10, then from 50 to 60, then from 100 to 110. And it will take those 3 black areas to construct the validation set, and all the remaining samples that are white to be concatenated to construct the test set. In your opinion, why is it the case that we have this structure with 3 diagonal stuff in the stratifold k-fold split? Here, recall that we are using the original iris dataset.
There's 3 different types of iris, right?
So,
Excuse me, 3 different classes of iris?
so there are 3 classes in iris, but even more important than this, yeah. In the original iris dataset, they are sorted. They are sorted by classes. So if we want to make sure that we balance and we have each class that is represented in the test set for each of the test sets we construct, we need to make sure that we do this. Because here we didn't do any kind of random permutation. So stratified k-fold, by default, is it's not random. It's like k-fold cross-validation. They are not random. So if you do not ask for a shuffle random permutation, they will try to preserve the order as much as possible. But stratified k-fold will preserve the order with the constraint that they want also to preserve the balancing of the classes. So it's try to deal with those 2 constraints at the same time. If we do the same with regular k-fold, then we have this that we did previously, and it is on the original data. And this is problematic. We can also do it with 10. The 10 is going to do many more splits. But this might be problematic. I think there is an example. Yeah, we will see that as an exercise. So I won't tell the answer to the exercise first. So we can also visualize other strategies like shuffle split. So shuffle split, you choose the number of split, like we did for k-fold. But we also select the size of the test set, as with train test split. So shuffle split is basically iterated shuffle train test split. So if we do that, you see this. And basically, we do not try to preserve the ordering. And we completely permute the order. And we just take 20% of the samples for the test set. And we take a random order 20% each time for each split. So there are still 5 rows in that matrix. But you see that it's completely random. And we can do a shuffle split with 20. And so we will train 20 different models independently of one another. But each time, 20% of the samples will be used for the validation set. Okay? So if you want to use one of those cross-validation objects, what you can do in scikit-learn is create the cross-validation strategy like this. You pass the parameters for the cross-validation. And then you store that as a CV object. And then to cross-val score, instead of passing 3 or 5 or 10 here, you pass the CV object itself, and the strategy is encoded there. By default, it will use k-fold cross-validation or stratifold k-fold cross-validation for classification. But if you want to use an alternate cross-validation, you can use this one. And here you see that we have this kind of result. If we use 20 iterations instead, we have 20 results. And then we can compute the average and standard deviation and so on. Okay, so the exercise now is use k-fold cross-validation, the standard k-fold cross-validation in the same way that we did here on the original Iris dataset without permutation and see what kind of score you get and how can you explain this. So let's try in 5 minutes. Maybe 2 minutes. Okay, let's see the result because I would just like to give you a highlight of the notebooks after that. So if we do the same with k-fold equals 3, and we use the original data without any shuffling, manual shuffling, then we get 0, 0, 0. So the accuracy of the model is completely bad. The worst that you can get. Why is it the case, in your opinion?
Because it trained on only one homogeneous thing. It encounters something that's never seen before.
So yeah, because in the validation set, you will see samples that you've never seen in the training set. If you see, for instance, here, I would use this. Recall that here it would be like 50. Yeah, 50 exactly. So it means that the class number 0 will be, all the samples from the class number 0 will be put in the test set for the first one. And the train set will be only samples from the class 1 and 2. So you always evaluate on something that you've never seen before. So you ask to predict a class that you cannot predict because you've never seen it. So it's really a pathological case in this case because we are exactly have the matching of the ordering that matches the split of the k-fold cross-validation. So you have to be aware of this kind of, if your data is ordered as some kind of dependency in the ordering, you have to be aware of this, otherwise you might be very surprised. So now we have k-fold cross-validation or cross-validation in general. It's interesting to combine this to be able to do some automated hyperparameter search. So I need to execute this. So very quickly. So typically, for many models in machine learning, there are some hyperparameters that control the model complexity. And if the model is not flexible enough, it will have a bad classification accuracy both on the training set and on the cross-validation accuracy, on the validation curve. So the green here is either the cross-validation score or the test score for a single 10 test split. And if you give more flexibility to the model, then it might be able to reach some kind of sweet spot. But if you give it too much flexibility, then it will start to memorize some noise from the training set. So the training set accuracy will go to 100% because it can memorize everything, including the noise. But then the decision boundary of that model will be very noisy. And on the test set, that noise is actually detrimental. And it's harming the ability of the model to generalize. It will memorize noise, and it's not useful for making good prediction on the test set. And so in that case, when we have a big gap between the train and test accuracy, we see that the model is overfitting. So here there is a gap between train and test. And here there is a gap between train and 100% accuracy. So here those are two different kind of gap. This one is called underfitting between train and 100 accuracy. And this one is overfitting between train and generalization. Okay, so the goal of machine learning is basically to find good modeling decisions to trade off overfitting and underfitting. And to do that automatically, we can either do it manually by doing the same kind of operation that we did previously and do cross-validation and doing cross-validation many times for different values of the hyperparameter. So these are the number of neighbors for the k-nearest neighbors regressor. And you see that for n equal 1, we have an average score which is close to 50%. N equals neighbors equals 5, we have some good value here. But if we increase too much, then we go below again. So here, in your opinion, which model is overfitting and which model is underfitting? One is overfitting and 20 is underfitting. Yes, it's a kind of counterintuitive because a small value for number of neighbors will give more flexibility to the model. It gives the flexibility to remember individual sample noise. Whereas with large number of neighbors, it will consider a larger fraction of the data set to make a single prediction. So it will have a very smooth decision boundary, and that might be also a problem, leading to underfitting. So this is actually underfitting, and this is overfitting. So to do this, we can do a plot where we see the evolution of number of neighbors, and we go in the reverse order, so that this plot is approximately matching this order, where here we have model complexity and accuracy. And you see that for the training set, when you increase the flexibility, the training accuracy goes to 100% accuracy. But then we have some kind of sweet spot for the generalization. And here we have a limit of n numbers equal 1, and we are overfitting here. Here we have a big gap, and we have a small gap, underfitting, overfitting. Okay? We have the same kind of problem with other models. This is a support vector regression. There are two hyperparameters, C and gamma. And you can see that for some values of C and gamma, we have a good score. Like this one is quite good, for instance. And or this one is even better. And for some combinations, it's very bad, like minus close to 0. And so here in this case, it's hard to tell that there is no single parameter that captures the complexity of the model. It's a combination of two hyperparameters. But in practice, gamma is very important, and then C can be important. But so it's hard to do this kind of analysis and pick up the best one manually. You would have to do a nested for loops for all the parameters. So what we can do instead is use this tool in Scikit-learn, where basically you give a grid of parameter values that you want to explore. Yep. And then you will wrap your support vector classifier or support vector regressor into this grid search object. And this is basically a way to automate the search for the good parameter combination for the model. So let's do this. We call fit. So this is what we call a meta estimator in scikit-learn, because it's an estimator that has a fit method that is wrapping another estimator that has also a fit method, but doing that many times. And at the end of this operation, you can make some prediction, and it's actually taking the best model that it found, retrained it on the full training set, and use that for the final model. So we can also introspect the best score that it found during the cross-validation procedure. So it's doing an internal cross-validation procedure. This is what is called grid search CV. CV is for cross-validation. And we can also have a look at the best parameter that were used for the support vector machine model internally. So this is a very useful procedure. There is an alternative in scikit-learn which is called randomized search CV. This is an alternative to grid search CV. The difference is that grid search CV will try all the possible combination, and randomized search CV is sampling parameters, because if you have many hyperparameters with many possible values, sometimes it's not tractable to try them all, so you have no choice but to take a random search, random combination. Yes?
Does Scikit-learn have other optimization routines built in, like steepest descents?
So there are two levels of optimization in scikit-learn. Either to train the tunable parameters from the support vector machines, for instance. So each of the models has its own optimizer internally. But there are also black box optimizers for the hyperparameters, like grid search CV, randomized search. And if you want smarter optimization routines for scikit-learn hyperparameters, you can have a look at what is called Scikit-optimize, which is a third-party project that is compatible with scikit-learn. It's also on GitHub, and it has some documentation. It's using additional models to find the hyperparameters of scikit-learn models. So for instance, you have GP minimize for Gaussian process. You can also use random forest from scikit-learn or Gaussian gradient boosted regression trees from scikit-learn to actually find the hyperparameters of another scikit-learn model. So it's a bit weird, but it's like nested optimization. One is optimizing the hyperparameter of another machine learning model. And basically, it's not using gradient information, and it deals also with the fact that you have noise in the cross-validation procedure, and it's kind of robust to that noise to find the optimal hyperparameters. So you have, for instance, this Bayes search CV, which is an alternative. It's a drop-in replacement for a grid search CV that has the same API, but will find the good hyperparameters. And there are several strategies inside. Okay, so just to have a look at the end, when you have those results, you can also have a look at the individual results using pandas by loading grid CV results. And you see for each parameter combination that were explored, param C, parameter gamma, the training time, the score time, the training cross-validation values, and so on. And so you can see everything that was computed and introspect it and do plots if you want to understand the behavior of your model. So I think we're going to stop here. Just maybe conclude on this diagram. So either you can, first you need to split your full training set into a training data subset and a final test data. This final test data, you never use it until the end, and you use it only once. If you cannot use it twice, because otherwise you're cheating. And so once you have done this train test split, you can do what we call nested cross-validation inside the training data to find a hyperparameter, for instance, using grid search CV, to do this procedure to find what is the best hyperparameters that you can use. You can repeat the cross-validation many times with different hyperparameters, then pick up the best parameter combination, and then finally evaluate it on the test data. And this is the final evaluation of your expected generalization ability of the model. And okay, I will stop here. There are many more notebooks if you're interested. And many of those notebooks are actually taken from examples from the book by Andreas Müller, who is the authors of this notebook. And so if you're interested in going further and having some more text narrative explanations on how to use scikit-learn, you can have a look at this book, which is called Machine Learning in Python, I think. Book, Andreas. It's Introduction to Machine Learning with Python. It's basically a book version of what we taught today with additional information, so if you're interested. And Andreas Müller is also one of the core developers of Scikit-learn. He's around the conference, you might see him. Okay. Thank you very much for your attention.